So we will begin with this keynote talk, and for this session we have Mr. Saveer, scientist F, IIT Lab Dehradun as our session chair, and we have uh, Dr. Mayank Dwivedi sir. We are privileged to have you amongst us, sir. Sir, Directorate of Industry Interface and Technology Management in DRDO headquarters. He is ME in Polymer Technology from DC, Delhi, and PhD in Advanced Composites from IIT Delhi. He is recipient of Gold Medal in ME. He is alumni of prestigious National Defense College, New Delhi. He has worked on major projects such as Agni Missile, BrahMos Missile, Warhead Technologies, and Biomechanical Devices. He has contributed to Indianization of high temperature resin systems and development of airframes. He has worked in identification and development of counterinsurgency technologies and products. He has spearheaded interactions with industries across the country for dissemination of policies for industries. He has number of international publications and patents to his credit. Also, he has delivered many lectures in various international and national forums. He has authored 3 books on nanotechnology and polymeric composites. He is recipient of Agni Award for Excellence in Self-Reliance in 2018 and Lab Scientist of the Year Award in DRDO in 2003. Sir, now I request you to kindly address the keynote talk.
Thank you.
Sir, I think I forget. Please give.
Now we would like to felicitate Dr. Mayank Dwivedi sir.
Sir,
Oh, sir, sorry, sir.
I think थोड़ा आगे चलो.
सर आगे जगह नहीं. आगे बोल रहा बोल.
प्रवीण जी.
Thank you very much for nice introduction. And for a change, I will not be showing you any presentation. Basically, my idea of the keynote address was that I will be delivering extempore talk, and there will be many faculties, etc. So I will be discussing about the various materials, so that I will like to enlighten you with the type of materials available, the futuristic materials, and what can you do with the materials. First of all, let me tell you, right now I am working as a director industry interface, but industry interface I am just working as one of the responsibility has been given to me, because after becoming senior you have to make some corporate director or some director somewhere. But as a matter of fact, I have spent my life completely in the materials only. I started my career in 1989 from Department of Science and Technology. My first posting was National Chemical Lab, Pune, in a chemical engineering division. And chemical engineering division, I am proud to tell you that first time polyurethane foam, puff refrigerator and polyurethane foam mattresses were made by my group only. I used to work with Professor Natkalni, and whatever polyurethane paints, etc., what not to talk about today in India, I am the one of the team member of the originator of polyurethanes in the country. Then after NCL, then I got selected for MTech, and then my GATE score was quite good. Then I wanted to do MTech from IIT Delhi. It so happened I was in some conference in Jaipur, and I had resigned by that time from DST, but my secretary, then Secretary DST, told me, Mayank, there is some very senior person is coming. He was director DRDL that time, Dr. Abdul Kalam, and as I am director today, and he is there, please go, and he wants one person to deliver a talk on polymers. So why don't you be there? So I delivered a talk, and my talk was at 11 o'clock. And my train, Marudhar Express from Jaipur to Kanpur. Though I belong to Kanpur, I did my first MSc, etc., everything was SBTI Kanpur. Then I had to go to Kanpur, unpack, then again pack for Delhi for MTech. Then Dr. Kalam listened to my talk and then he told me, I need you, you join me immediately. I said, sir, I cannot join you, I have to do my MTech, etc. and my career is there. Well, I will make you do many MTechs. You come and join me because I do not have any polymer scientists with me. So that's how my journey started with DRDO from 1992. So why I have told you this story, because I just wanted to bring your interest that I am not coming from the corporate headquarters who will talk about only the policies and how to go about it, because I know you are a student. I was also a student once upon a time. So that's how the story begins. First of all, I want to thank the organizers for inviting me, specifically the faculty sitting here. He was pursuing me that I must come. I am really grateful to Dr. Salva Murthy, who is my senior. He was Director General in DRDO. He came to my office specifically and extended the invitation. So to entire MIT management, I am very thankful that I have been given this opportunity. One thing I will tell you, any lecture, whenever you listen to, any literature you read to, let it be any literature, with a positive mind frame, if you listen to a positive mind frame, you read it, always you gain something. And usually so happens the lecturer who is in front of you, probably you do not get a second time to listen to him in your lifetime. Usually it happens. That is the statistical data. I do not say it always happens, but it usually happens. So my kind request would be that I will be delivering a talk for 20-30 minutes, and you may ask questions also, and you listen to me carefully. Reason I tell you why, because I have that almost 32 or 34 years of vast experience in materials, and I will be very happy that if I am able to help you out in some of the things. So let me first tell you, you know the material, matter is something which occupies a space, has the mass, etc. Also definition we have studied. But when we talk about the materials, then you be very, very careful about one thing. आप लोग बात मत करो, बात करनी तो बाहर जाके करो. So materials are the medium to transform our ideas, your concepts, your designs into reality. If materials are not there, you cannot convert your ideas into reality in a product, a tangible product. Similarly, akin to it, if alphabets are not there, you are not able to use the alphabets properly, then you cannot write any prose or any poetry or any other piece of good literature. That's how the ingenuity of you as an engineer lies, that how do you use material to make the best use out of it. For example, had Shakespeare not been there, then we did not know how to make such a beautiful literature. So Shakespeare knew how to use those 26 alphabets. If those 26 alphabets are given to you and me, we cannot replace Shakespeare. So the point is, materials are 118 as per the periodic table, when 94 are the natural occurring elements and remaining are the man-made elements out of those 94. But it is not that. It is that how do you use those elements for your benefit. The point is, like we talk about lithium, which is very important thing nowadays, about lithium ion battery or lithium polymer battery, etc. But what happens? When lithium was only as an element being used, then what used to happen? That lithium was only for the metallurgy purpose, for a glass clearance purpose, or so many other things lithium was being used. But it was the ingenuity of the scientists, the understanding of the scientists, how to use lithium, so lithium polymer battery can be made. Another example, the rare earths. The rare earth was also the same thing. The rare earth, we earlier thought that they are something in the earth crust, etc., and how can be used and what mass can be used. But finally, when you started using the rare earths for the nuclear systems, then you made the fissile material plutonium and uranium-235 finally it came out, then you realize that potential of this. These are some one or two examples, just I told you that it is your ingenuity how you use the materials. The materials right now what they exist in abundance in the world, they are natural as well as synthetic. The natural materials like metals, wood, leather, etc., they are still there. Basically, primarily if you talk about the polymer science or all the synthetic materials or composites, primarily the background from where I come from, those composites, etc., and all the polymeric material were made just to replace the naturally occurring material, because we thought that resources are limited. And the material is so important, as you will appreciate, even our societies were known by the name of the materials. The Stone Age, Iron Age, Bronze Age, all these ages were there what? Because of the material were having so much importance. But nevertheless, as many synthetic materials we have made, the sheen of the natural occurring materials, so-called metals, has not gone from our mind. But then you say, then very logical question comes, when the naturally occurring materials like metals etc. have got so much potential, then where was the necessity to make composites and other lightweight materials? Here the story begins. If very very precisely you go through the history, because you must know also how the materials have originated in this form. The Second World War was the first origin of the development or research and development of the newer materials. And ironically, let me tell you, it is something very much associated with the wars. When you talk about the first industrial revolution after the First World War occurred, then when the Second World War came, that time again the revolution of the materials occurred. It means the materials probably fulfill the requirements of the World Armed Forces, and that's how these materials were required. So I just give you the example how the composites came in picture. Composites came in picture because Royal Air Force, they were using the aircrafts and they had the radome to protect the antenna part. They used to use a plywood in 1940s. But they were finding when a rainy season anything is there, the radome performance was getting deteriorated because when electromagnetic radiation passing through a dielectric medium, in this dielectric medium some ionization occurs because of water, because the plywood was absorbing the water. Then the signal, the attenuation of EM wave was too much, and the attenuation was not able to detect the communicate and detect the target properly, and that's how the problem started. So they told there should be some material which should be hydrophobic, not like wood, which will absorb water, and so that the quality of the communication and the performance of the pilot and the operational capability, operational performance of the pilot becomes much better. So the performance of the pilot becomes much better, and that's how the first time the radome was made. And this radome, which you see in the every aircraft nose cone, missile nose cone, it is nothing a nose cone. It is the aerodynamic structure, as well as this is transmitting the electromagnetic signal so that the pilot is able to manage, because it is you can say it is a spectacle over the eyes of the antenna. So that's how the origin of the advanced material started, and that's how the rubbers came, as all these things came. Even when the Dunlop made the first tube, that time also that the material was that cotton reinforced rubber or some nesto rubber base. Finally today you see butylene tires and tubeless tires etc. All those evolved out of the synthetic materials. But there are certain things, had these advanced material been not there, our life would have been very miserable. The first thing comes to missiles. Had the advanced composite not been there, then we would have not been able to fly the missiles, space shuttles, etc. Because what happens when any rocket is being fired, the rocket motor inside temperature is between 2000 degrees Celsius to 2500 degrees Celsius. And at that high temperature, no material can exist. If you want to use tungsten, etc., then it's forging, machining, etc., in the form of rocket motor is very difficult. Its weight is so high. So then your dead weight will be so much that your warhead capacity, weight will come down. So it is not a viable solution. So when first time the ablative liners, they are the materials where when high temperature is there, then they create a rather you can say insulative wall between the metal outside, because metal is required for the structural purposes, for structural strength is required, and the inside is a rocket motor lining out of composites using Rocasin rubber, EPDM or silica fiber with glass phenolic resin, and that's how they protect the complete structure. And the beauty you see, within 50 mm of thickness of glass phenolic composite, the inside temperature is 2500 degrees Celsius and outside temperature is just less than 50 degrees Celsius. Within 50 mm wall, that type of insulation is provided, and the density of that material is less than 2. So this is the beauty, less than 2 gram per cc. As a matter of fact, when Agni missile re-enters in the atmosphere, the outside temperature reaches to the extent of 3000 degrees Celsius. And that time, all the control, guidance and stuff, whatever there inside the missile, that has to be intact. So that the right time when, as per the onboard computer command, the signal is given, the warhead has to blast. Suppose the electron circuitry is not working due to high temperature, then Agni mission would be failed. So that's how these composites came in picture. And that's how the nozzles, the airframes, like Dreamliner aircraft, B-52 bomber aircraft, all these things you find, the composites have played very, very important role. But this is the one good thing I have told the composites, because I am a composites man, I will speak very good things about composites. But there are some problems also. You cannot make very good hinges out of composites. There is a big problem joining composites with the metals. I have published one paper in adhesives. It is, I think, Taylor and Francis or Wiley. And there I try to solve that problem. But now, because most of you are a mechanical engineer, so I think you will appreciate. What happens, whenever you are going with a composite with any adhesion, etc., the very important thing what plays in everybody's mind is the strain. At the load, what strain, what deformation is occurring in the metal and what deformation is occurring in the brittle material like composite, there is no match. So what happens, first you have to measure the strain, and when you talk about the strain, then you have to measure the modulus also. Because the modulus, when you will meet, then only the stress upon strain will come in picture, na? So means your strength might be good, like you talk about a mild steel, then your strength is 400 MPa. When you are using composite, strength goes up to 600 to 800 MPa. If you are using very good carbon composite, it goes to even 1000 MPa and plus. So your strength is not a problem. But within the yield, before the yield point, whatever workable stresses are there, suppose you want to work at 300 megapascal. The 300 megapascal, whatever the strain steel will experience and whatever the strain composite will experience, there will be mismatch. And this mismatch will lead to fracture. So how to do it? Then there are the technologies where you make the intermediate layers where your modulus mismatch is gradually reduced, so that what happens when the composite, the load is transferred from fiber to fiber or lamina to lamina, then there is a bond in such a way so that it is a sort of a flexible like a rubber type of pad, so that it is gradually changing and it is not causing sudden fracture because there is a transition. So these are the technologies we work, and that's how as a mechanical engineer, see I tell you, today I give you the example of DRDO. Most of the mechanical system what we do, everything is being done by the industries very aptly. Talk about the launchers, talk about the bridging system, talk about the other unmanned ground vehicles, talk about the engines, chassis, tank, hulls, anything you talk, everything is being done. Because these are now the established technologies. Because only one thing the human being knows very well, because we are working on the metals from the ages, I think 5,000-7,000 years back. Metal, we had the experience. How to handle the metals, we are very comfortable. Whenever you go to any welder, any shop, you say ki there's a problem in this, some problem there in cycle, bicycle or car or anything. If metal thing is there, the denter and painter says, I will ठीक कर दूंगा. But the moment you bring the composite car, you make a fender, then he will say, I do not know what to do. I will do some stitching with the wire, and I will do some putty, etc. But he does not know how to join the composite because the knowledge is not there. Now for the plastic, that knowledge is not there. So that's how these are the advanced materials, and when you being the mechanical engineers, probably if you are going to be in structures or any other related branch, then finally the composites are going to be the mainstay for you. Not only composites, even the polymers also. But here one more issue comes, which I would like to touch upon. That the biodegradability factor. Because the biodegradability of the composites, of the polymers and plastics is very poor. And now the people have come out with very fine ideas. Then initially they told no, with the polyethylene and polypropylene, we will mix the starch. The starch will biodegrade, and finally the entire polythene will become powder, pulverized, in micro size thing. Then it will be very safe. We did it. Finally, we found the fish, animals, even a human body. Recently, I read in the newspaper Times of India, even the microgram traces were found in the human blood also of the microplastics. Then the issue came, how to sort it out. I mean, let me tell you, for your kind information, whenever you are using the RO water at home, please tell your parents, everybody, your surrounding, RO water should never, never, never be stored in plastic bottles. Let me any Tupperware or any nonsense. The RO water should be stored either in glass bottles or metal bottles. Otherwise, it's better that always use glass bottle only, but no plastic bottle. Why I tell you? Again, I will come to that biodegradability later on, but this is a very important piece of information I want to tell you as a material scientist. Because in RO water, you leach all the necessary minerals, what should be there usually in the water. The moment you deprive water of those minerals, the moment it goes to plastic environment, plastic is never made alone. Plastic, there are always some fillers and processing aids. So it starts leaching them in the water. And finally what happens, the water you are drinking, there all those chemicals come in the body, and that's how the plastic bottle uses is not good. They cause the metabolic disorder and lead to cancers. So these things are important. So when this pulverized polyethylene did not work, then people thought, no, we will go to PLA, polylactic acid. But polylactic acid, again the issues were there, it was very costly, as well as the degradability and processing, all the things were time taking. Then finally the new material which is being used in the world market, where in India we have also launched, DRDO has also done a lot of research and made it, there is the PBAT, PBAT. And PBAT is now the thing where the nano clay is being reinforced, and that's how the biodegradable bags are being made, and this is completely compostable. So that's how, let me tell you, there are more than 2 lakhs polymers and their blends in the world. And myriad of possibilities are there. You talk, anything is possible except hinges and abrasion surfaces out of composites of plastics. Otherwise, everything is possible. Those things you have to go for the metals. This is one part I told. This is a very important thing, and I think you must concentrate about the materials, because unless you understand the material, your design is never complete. Because design, when you are putting the structure, properties, etc., then you must know the material what you are dealing with. If you do not know about the material, the designing and the exotic designs are not possible. This is the one part that, because materials I want to speak, I can speak hours, because materials are so vast, there is no end. Secondly, comes to the metal alloys. Let me tell you, in India today, again we are very much deprived of good quality of metal alloys. Still we are importing many steel alloys from Germany, from Japan, some from China. Rare earth magnets, though we have got very strong rare earth deposit in India, I think we are number 4th in the world. But probably our policies are such that rare earth can be extracted only by the government agency like IREL and NMDC, etc. That's why we are not able to extract the full potential of rare earth. As well, rare earth and some of the metals we are good, but most of the metal alloys we are not doing very well. Then let me tell you, it is very easy to talk about engineering and technology, what you are studying. But let me tell you, friends, you must understand the science first. And many times what happens, well, I go for the campus selection and all, your institute is quite good, you might be taught everything, so I am not questioning you. But usually what happens, I find, then people do not understand the difference between science, engineering and technology. This difference is very much important. Unless you know the science well, you cannot do the engineering. Because application of science is engineering. And many times what happens, the scientific principle we are not understanding, it becomes a problem. And technology is the application of engineering where the cost effectiveness, user's requirement, where repetitive quality is taken care of. That is technology. Okay, I will not go into those definitions. But whenever you are trying to address the materials issue, the science is very important. That's why people many times say material science. Do not say materials engineering. Because material engineering is automatically the offshoot of the material science. So, material alloys, if you try to understand, have you thought why we are not able to find the solution for the material alloys in India? Still we are importing. The game is what? I will give you one example. Why I am giving them, because I have written a textbook, there also I have given so many such examples, so that it will not rest in your mind if I talk about the science and equations. If I talk about some examples, it will rest in your mind. Like you see the bronze. वो मंदिर की घंटी बनाते हैं ना, whenever you see the temple's bell, all are made of bronze. Bronze is called bell material also, bell metal also. What happens there? There is a copper and zinc like brass, but out of brass we do not make it. Then what we do, there we mix some tin also. For example, just I'm giving so that the moment to mix tin, then it becomes the bronze. And when the bronze is there, then it becomes the bell material. How to bell material? Because the moment you hit it, when whatever sound comes out, that sound will keep on coming for a longer duration. Again, there is science, because the electrons, whatever they're inside in the copper, because of tin, they are trapped there. So they oscillate and vibrate only that place. Whereas in brass will make the bell, the moment you will hit it, the sound will come, but duration will not be that long, because the brass, the copper electron, they will be circulating around copper and zinc both. But the moment the third element has come, tin, this has restricted the movement, that's how the energy was not dissipated. So that's how the bell material came in picture. Similarly, keeping these three metals in an alloy form in a solution, we call it solid solution, you must have studied in your mechanical engineering. Keeping them in a solution form at the room temperature, whatever operational temperature, is the science, is the technology. It's not science, rather it's a technology. So how to develop that understanding to keep that alloy at that room temperature or their work service temperature intact is the beauty. Like example, you must be using copper alloy, copper based aluminum alloy, जिसे हम लोग कहते हैं ड्यूरा एल्यूमिन और 2014 और 2017 grade of aluminium is very good aluminium. Its tensile strength is similar to steel. Steel is 400 megapascal. It is I think some 350 or 375 megapascal. Why it is good? Very good, because the copper alloy is there. There is only 4% copper in the aluminium. It makes it like a steel, but it's very difficult to handle. The moment you heat it, the copper precipitates out. Then it becomes useless aluminium, where the 200 or 150 megapascal tensile strength is there. The point is how to keep that solution intact at that temperature or working temperature is the technology. That's why we talk about the TIG welding, MIG welding, etc. for the copper, so that we create the inert atmosphere so that welding is there, and that's how copper, before it comes out, it welds and we come out of it, oxidation does not take place. So this is the thing. Then third thing I will like to just touch upon, टाइम में बचे 3-4 मिनट तो मुझे आप बता देना, 5 मिनट्स में बस बता देता हूँ. Third thing I will like to touch upon, you must pay attention on ceramics also. They are another very important materials, the advanced ceramics. And advanced ceramics, let me tell you, let it be silicon carbide, alumina, boron carbide, anything you talk about, they are really exotic material. And let me again tell you, the mechanical engineer's life is not that easy without the carbides. Because all the high-speed tools, all the machining tools, etc., somewhere we are using carbides. And that's how the silicon carbide, boron nitride, alumina, etc., they are very hard materials. They do not have much strength. But yes, there are certain advanced ceramics, or not fine ceramics, advanced ceramics, where they are machinable also, and there their properties have been increased to the extent where you can have variety of operations. Now, one of my lab is there, DMSRD Kanpur. They are using, they have developed a technology using a polycarbocyanide. They are making a boron carbide fiber. Let me tell you, the day the boron carbide fiber, a good boron carbide fiber comes in the market and it becomes a reality, it is going to shake the world, because that fiber is going to replace all the existing technical textile like carbon fiber, glass fiber, Kevlar fiber, what not you talk about. So these are the things I just want to tell about, tell you all about. Lastly, I will just, because 2 or 3 minutes, I will touch upon one more material for the sake of your understanding, that high energy materials, explosives and propellant, they are also very important, because they also play very important role in the sense RDX, HMX, TNT, CL-20, which is the world's top class explosive, China Lake 20, that has been developed by India, and right now I think 2 or 3 countries are manufacturing it, and India's CL-20 is rather, I may say, is one of the best as far as quality is concerned and the performance is concerned. In the rocket motors, if you talk about the hydroxyl terminated butadiene, rubber, and various other NC, NG type of combination, everywhere we have mastered. Today you should take pride that today all the rocket motors are of indigenous origin. We do not import even a micron thing from abroad. There's 100% rocket motors for ISRO to DRDO and Agni missile to any system is our own. All the explosive, all the warheads are of our own origin, and that's how all the pyrotechnic, etc. we have mastered, and that's how we have come up so well in this area. Also, most of the HMX and RDX and most of the explosive in America, Germany, France, and to some extent England are being used, manufactured by India. The Indian companies based on DRDO technology, they are supplying them. So all put together, let me tell you at last, it's a very exotic area of material science, and for the mechanical engineers it's much more close to their heart, because finally if I talk about the electronics engineering also, whatever the VLSI design etc. you do, the gallium nitride, gallium arsenide, all these wafers you require, nothing is possible without materials. How to use the materials aptly, that is up to you, ingenuity of yours, and your understanding about them will certainly enable you to make better designs. If any questions that you ask me, thank you, Jai Hind.
Thank you, sir, for such an informative talk. I am sure all the guests and esteemed audience are able to take back something valuable. Now, I would like to request Mr. Shabir Ahmed, sir, to kindly present memento to Dr. Mayank Dwivedi, sir. Can we have a huge round of applause, please? Now I would like to request our HOD sir to present token of gratitude to session chair Mr. Shabir Ahmed.
Please, Dr. Gul.
Thank you, sir.
Thank you very much for patience. And sometime else, if your session is going on, not just as a guest lecture, just as a guest faculty, you invite me.
Yes, sir.
And I will come
Sure,
and give
sure.
a talk.
Sir will also come in sometimes to teach you. Like
और teaching के लिए आपसे बुला लेना मैं आता हूँ.
yes, sir. Yes. Sir,
I request all the students to please be seated. Actually, we cannot replace the.
As we proceed on to this keynote talk, I would like to invite the session chair for this talk, Dr. Nikhil Dev, to kindly felicitate Dr. Afzal Hussain. Can we have a huge round of applause? Thank you, sir. Thank you, sir. We are privileged to have among us Dr. Afzal Hussain, sir. He has received a PhD degree in mechanical engineering with a major in thermodynamics and fluid mechanics at Inha University, Incheon, South Korea. He had worked as a full-time lecturer in the Department of Mechanical Engineering at Inha University from March 2010 to August 2012 since September. Since September 2012, he is working in the Mechanical and Industrial Engineering Department, Sultan Qaboos University. His research interests are multidisciplinary in the broader area of thermos, fluid, and CFD. He has published more than 90 research papers in peer-reviewed international journals and conferences. Sir, now I request you to kindly address the keynote talk.
Welcome all, and thank you so much for giving me this opportunity to present my work before you. So, the topic of today's talk is electronics cooling, and in the specific area of like how we move in the electronics cooling, starting from the natural cooling of electronics to the like force cooling, liquid cooling, and the other from conventional way to the innovative ways of cooling. So this talk is basically a journey starting from the beginning. I started this research from almost 15 years back, and then we moved slowly, and with the help of other colleagues and students, we able to progress in this area. So I will present before you like how and what we have done so far to basically mitigate the heat dissipation from the electrons. So if you see, as you know, like how we are cooling the data centers and how we are cooling the computers and the heating problem in the mobiles and laptops, etc. So starting from like we want to cool the chip, and the chip is very, very small. So how we can cool the chip where the heat dissipation is very high, so of the order of like 100 to even 200, 300 and more watts per centimeter square area, so which is very high. Like if you compare it closer to the power plant, then it reaches closer to the nuclear power generation. So in the beginning, when the number of transistors in a chip were very small, and then it was not required to cool the chip using the non-conventional ways, and it can be cooled naturally and sometimes by forced convection through air. But over the time, when the number of transistors in a chip increased, and nowadays when you see the integrated chips, it's highly dense, and there are millions and billions of transistors inside the very small chip, and that dissipate a lot of heat. So if you see the trend here, then you will realize that how the number of transistors are increasing in a very small chip. And when the number of transistors increasing, then the heat dissipation is also increasing. So what is the temperature that we want to keep the chip for its proper functioning so that it can have a longer life and it can sustain as well. So here we have a range that we can maintain the chip at 40-50 degrees Celsius, and at the most we can go to up 80 degrees Celsius. And then the heat dissipation over the chip surface, if you go over the years, then we see like the heat dissipation from the chip is continuously increasing due to the high density of transistors that the chip consists of. So what is the reason of the electronics failure? If you look at then the major part of the failure of the electronics is the temperature, and including other like the humidity, dust, and vibration of the electronics as well. So how to control this temperature of the electronics, and how we can mitigate the temperature rise? So there are different techniques, like you can put a heat sink over the chip surface, and then if you want to further enhance the capacity of the heat sink, then we look for that what are the conventional ways of increasing the heat transfer rate from the chip surface and applying some non-conventional techniques to mitigate the temperature. So there are some techniques which were before used for conventional systems like your radiators and other condensers. So those techniques, we try to implement them at micro level, at the chip scale level. So these techniques include like surface roughness and surface enhancements, jet cooling, and the scaling down the size of the flow channel so that we can have the scale effect for the heat transfer enhancement. So these are the advantages, like when we talk about the microchannel. So when you try to reduce the size of the heat transfer device, then what we want to do is we want to enhance the surface area and we want to reduce the volume. So as long as we have the high aspect ratio of surface area to volume, that means we are moving towards the higher heat transfer rate. The other area of heat transfer enhancement is the jet. So when you impinge a jet on a hot surface, then it takes larger amount of heat from the chip surface or from any hot surface. The reason is that it forms a very thin boundary layer, and that has a very high heat transfer coefficient. So if you see this disassembled view of the chip and the heat spreader, so here you see that a chip, open chip, and then we see that the chip is very small, and over the chip we put the spreader, and over the spreader we put the heat sink, and that heat sink is basically dissipating the heat to the environment. So, but it has a limiting capacity. As we know, like the number of transistors are increasing and the flux generated at the chip surface is high, so the natural convection is not sufficient to remove the heat, and then we use the fan over the heat sink. And after that, even the fan was not enough, so we put the cold plate over the chip surface so that we are flowing the liquid, and the liquid, as it has higher heat carrying capacity, so the liquid can remove the heat from the chip surface. So, but that was not the end of the story. So as the number of transistors further enhanced, and then we need to remove the heat, further heat from the chip surface, and we need to keep the chip down to the working temperature, then what is proposed that we go to the chip itself and then cool the chip itself through the liquid cooling. So how we can cool a chip which is very, very small, like 1 centimeter by 1 centimeter in area, using liquid? So this can be done by engraving the grooves over the chip surface and making some channels over the chip surface. As you can see here, we can make simply the rectangular channel or any shape of channels, and if we are able to flow liquid through those channels, and then because of the scale effect, the heat transfer coefficient is very high. So I hope you are getting the talk, because we are talking about the heat transfer coefficient and the heat transfer area. So as you scale down the fluid channel, and the hydraulic diameters goes down, and that takes that basically contribute to the very high heat transfer coefficient. So scaling down and making the micro channels, the advantage is that we get the very high heat transfer coefficient, and that can take away higher heat flux. So again, like the story didn't end here. So the rectangular channels, they have again a limitation. So we want to further enhance the heat transfer. So how can we further enhance? So there we go to change from conventional rectangular channel to different sort of channels. Like it can be rectangular, it can be triangular channels, it can be trapezoidal channels, and it can be oval or circular channels. And then we look for, like in conventional heat exchangers and in like conventional size heat exchangers, how do we enhance the heat transfer? So we looked at those ways, and then we tried to implement those mechanism into the micro scale geometry, and that can be passive enhancement. And the passive enhancement, that we want to perturbate the flow, and that perturbation enhances the mixing of the flow, and that enhances the heat transfer coefficient. So one of the ways are like you are putting the roughness on the surface, you are putting the pins on the surface, you are putting some obstacles on the flow passages, so that can disrupt the flow and that can enhance the heat transfer. So these were the work we did in the beginning, and then we published those works, and these show some promising results, like basically the heat transfer is enhanced and the capacity of the chip to cool down is increased. So these are some designs we tried, that we did the different sort of passive enhancement mechanism. Sometimes we put ribs, sometimes we put the obstacles on the floor, and sometimes we made the walls wavy, and sometimes we put grooves on the wall to enhance the heat transfer. So these are all this is all the summary of the different mechanism that we adopted to enhance the heat transfer. Then we moved to the jet impingement. The reason was that, like when you have a channel, micro channel, for example, and the liquid is flowing from one end to other end, and then at the entrance, when your liquid is at low temperature and the chip is at high temperature, the temperature gradient is high, so the heat transfer rate is high. And as the liquid goes from one end to other end, the liquid gets heat up, and the temperature difference becomes smaller, so the heat transfer coefficient and the heat carrying capacity towards the exit was low. So at the chip surface, it generates the temperature gradient. At the inlet side, the temperature was higher, and at the outlet side, the temperature was lower, and at the outlet side, the temperature was higher. So that creates a temperature gradient on the chip surface. So that gradient is again harmful, because to keep the chip safe, both are necessary, the temperature gradient as well as the temperature. So how to mitigate this temperature gradient? So for that purpose, what is proposed, that we should do the jet impingement, we should do the liquid impingement at different locations of the chip, so that the gradient can be decreased. So that brings the development of the jet impingement cooling for the chip surface and for the electronics. So the different designs were proposed, and our group also proposed different designs. So that were, we can have a different size jet holes, and we can have a different arrangement of the jet holes, and we can have a different arrangement for the exit of the liquid that has already fallen onto the chip, and that has already strike the chip to cool the chip, and then we have to remove that liquid. So the one thing is that how basically you are striking the liquid on the chip surface, and the other thing is that how you are basically taking that liquid out of the chip surface, because that liquid has already been heated up. So different mechanism was proposed, and as you can see here, like the one way you are striking it, and other way you are taking that liquid out of the chip surface. And remember that all of these were proposed at the micro level. So where the dimensions of the holes are in micron, like 100, 200, 300 microns, so depending upon the fabrication technology. So this jet impingement proved beneficial in terms of reducing the temperature gradient as well as unifying the temperature at the chip surface to some extent. So here are some possible combinations that we did. That in the first slide, if you see that there were jet impingement, and the another slide you see that there are jet impingement as well as jet extraction holes. And the third slide, if you see, like in the third diagram, you see like there are jets, but the exits are from all around. So we tried the different combinations, and then we looked at like what combination fits well for the chip. And here you see like there is a big jet that is striking the chip, and then there are small holes that is taking the liquid out. So if you see here that the big jet at the center, that is basically the impinging the chip, and then the small holes that is basically taking the liquid out of the chip domain. So we did all of this study numerically mostly, and we did some experiments to verify our numerical model from the existing experimental studies as well as our experimental study. So again, like we want to further enhance the heat transfer rate, and then what we can do. So we implemented and the passive enhancement methodology as well as the jet impingement. So the passive enhancement that to perturbate the flow and that can enhance the heat transfer, and the jet impingement that can basically create a stagnation zone, and then it can create a thin boundary layer so that can enhance the heat transfer. So we propose the hybrid design, and that includes the passive as well as jet impingement technology for this in the same chip module, as you can see here. So this was also showed a good result, and decreased the chip temperature. Further, we looked at like we are striking the jet on the chip surface, so what angle can be the best suitable angle. So we looked at the parameterization of the angle and looked at like what angle can be a best angle for the chip cooling. And currently what we are doing is like we are trying to implement the porous material inside the channels. Like once you group the channels, and as we know, like the porous material that has high capacity for heat transfer because of the pores inside the material, and that gives us high surface area, and that surface area basically leads to high heat transfer rate. So if we insert the porous material, and that increases the heat transfer, but the disadvantage for the porous material is that like it creates a lot of pressure drop. So when you are talking about the mini scale or micro scale, and when you are putting a porous material in a channel, so that creates a lot of pressure drop. So how to basically optimize that, how much porous material you should use and where you should use. So that kind of a study that we are doing currently, and which so as you can see here, like different scenarios, that in the channel we do not have any porous material. In the second, we have the porous material completely filled the channel, and then we have the porous material that is lying on the bed, and another that is lying on the side, and the fifth case that we have a porous material in the direction on the way in the direction of the flow. So that is at the intermittent locations. So we studied all these scenarios and then looked at like and then put into that spectrum like what is the best possible option for these porous material inserts in the channel. So for all these, like if we looked at the numerical methodology, the flow is laminar flow because it's a micro scale and very low speed flow. So and the flow is steady, and because the liquid is flowing in the channel, so it's incompressible. So we applied a steady state laminar incompressible flow model, and we use the commercial software that ANSYS. We use CFX as well as we use Fluent to solve these kind of problems. And so here are some results, like when there are parallel channels, there were no perturbations in the fluid. So we see that the upper picture, the temperature is higher on the chip, and we obtained a lower temperature when we use the roughened surface and when we use the perturbators in the channel. And the same case is there, that we have the higher temperature when it's a smooth channel, and when we obtain the lower temperature when we use the rough channel. And here, like when we have the wavy walls in the microchannels, and the grooves are cut on the side walls, and then we see that where the temperature is significantly lower, as you can see that the top line indicating that when your channel is smooth, and then the bottom line is indicating that that is some combination of the this group parameters, and that gives the minimum temperature of the chip. So this is the improvement that we got for the chip cooling. And further, like when we did the pin-fin designs, and then we look for the different combinations, like the one is the parallel, that is the oblique fin parallel, another is the oblique fin offset, and then another is rectangular fin offset, and then the rectangular parallel. So in all combinations, that the oblique offset pin fin shows the best result. So as for the jet impingement, if we see, so we looked at the temperature profile and the velocity profiles. So here we see that how this velocity goes, that where the jet is impinging on the surface, and then the liquid is coming. So the liquid is coming from the different jets, and these different jets accumulating the liquid, so the velocity is higher at near the outlet. But the disadvantage with this multiple jet impingement is that, like in the beginning of the jets, like when we talk about towards the inlet, the jets are striking at the base. But as we go downstream, the jets are not striking at the base, because the fluid is coming from the downstream, from upstream jets, is basically flooding the jets that are on the downstream side. So again, like this is the problem that we have to eradicate. If we look at the temperatures, and then we can see that the different combinations and different sizes of the jet, and that we did the parameterization to basically see the best possible option for the temperature minimization, depending upon that what should be the jet size and what should be the pitch of the jet. So here are some results, and so here are further some results that shows the what possible combination can be the best suitable for minimizing the chip temperature. So these are some results that we have, and all of these results shows that the techniques that we implemented is somehow benefited to reduce the temperature, and that can give say the electronic designer a chance that to further enhance the your transistor, let's say to increase the transistor density in the chip. So the development of the thermal management goes parallel with the design of the integrated chip. So the integrated chip is over the time integrating more and more transistors. So as a thermal management engineer, we have to manage that how we can reduce the required amount of heat from the chip surface. So this is the development that I showed you over the years that we done through our research, and here are some results as you see here. So if I conclude this, that if we have the roughened channel and if we have the perturbations in the channel, so that gives the benefit and that gives the advantage of higher heat transfer. And if we have the multiple jets, so that gives us the more uniform chip surface temperature, and that increases the that decreases the temperature also. And at the same time, if on the chip somewhere there is any hot spot, so the jet impingement can mitigate that hot spot as well. And if we have the effusion holes with the jet impingement, so that also provide an advantage, and because once the liquid is striked on the jet, and then if you want to remove that liquid, so it can be removed through the effusion holes. So when we have the combination of a hybrid design, that is the jet impingement as well as the passive enhancement, so that is basically the you are basically employing the three technologies, that you are applying the microchannel technology as well as you are applying the passive enhancement technology and jet impingement technology. And when you have the porous slabs, so the porous slabs, like you have to be very wise how to use the porous slabs, because the porous material inside the channel increases the pressure drop, so it cannot be used blindly. So, and where it can be used, a proper combination and the placement of the porous material is important to reduce the pressure drop as well as get the advantage of higher heat transfer. So I presented a broad picture without going into the intricate details of the model and intricate details of the results, so that because I know that it's a general audience, and if I go into the detail, it may not be understood. And so if you have any questions, please let me know. And if you want to know any further detail about the modeling, about the design, you can contact me. Thank you very much for your patience. And if you have any question, please let me know. Yeah, the heat transfer coefficient is directly responsible for increasing the rate of heat transfer. Q.
Like in the phone, the battery or heat is really the chip uses. Like in the iPhone and versus the Android phone,
Yeah.
the heat is transferring from the phone.
That the heat is coming out of the phone, you mean?
Sir, the difference between the iPhone and the Android, the chip they are using, will affect the heat transfer enhancement or not?
It depends upon that how much heat is generating, first of all, the chip. If it is not same, they may be generating different heat, right? Different heat flux. And again, that what is the mechanism of heat removal? An iPhone is different than the any other mobile. So depending upon the how much capacity your processor is, so how many number of transistors it consists of. So the heat generation is directly related to the number of transistors. Yeah. Yeah, please. Yeah. It is. Yeah. Yeah, like as of today, the direct chip surface and grooving and micro channeling is not in the market. So what they are doing basically, they are doing that they are putting a spreader over the chip, or they are putting a cold plate over the chip, and in that cold plate basically they are implementing these techniques. Like I showed you the open model. Yeah, heat sinks, like, yeah, I'm calling it cold plates. It's basically heat sink, like this one. So over the chip they are putting the heat sink, and they are implementing these techniques on this cold plate. So this cold plate is having the micro channels. It can have a micro channels, it can have a jet impingement, and it can have like any of the techniques that I showed you. But directly on the microchip, like here, directly on the microchip, it is still not in the market. Yeah, it is under research, because the silicon based, because the chip is silicon chip, so the microchannel on the silicon, it is not in the market. So what they are doing, they are putting a spreader, and then they're putting the cold plate over it, like in the left picture, we see the spreader in the left picture. So the chip is inside it. Like this is the flip picture. Like if you see here, this one is flip picture. This one, right? So we are putting the heat sink over it at present.
But this technique, I'm very much sure that my complete electronics organs are well intact. But using the other way around, if you have shown the earlier part, it will give a little bit of
You mean like when the channels are on the chip itself?
The one which you showed earlier to me.
Which picture?
This one.
This one.
Yeah.
Depending, but I don't think so because it's a very compact structure.
It's a commercial chip.
It's a commercial. It's commercial plate basically, cold plate. We call it cold plate and we call it heat sink. It's commercial. It's now coming like high-end workstations or high-end computers, like which is like multi-core, like.
Generally, military grade components. Are these available in military grade? Are you aware about military grade?
I'm not sure about the military grade, like the HP range of workstations. The higher end one, they are using this liquid cooling, but it's still the lower end one, they are still relying on the fan based. But the higher end one, that they are using the liquid cooling workstations. So that may have like multiple processors, maybe like 16 processors or more even. The laptops are normally they are based on the heat pipe cooling, phase change cooling. So they have a heat pipe system and then they attached it and they cool it. And the other way that they use the fan cooling. There is no liquid cooling in some laptops. In high-end laptops, they use the heat pipe system cooling. If you are aware of that, like, yeah. So it depends upon the design. Like as I said, like the liquid cooling is efficient, and as well as like the heat pipe cooling, that is also efficient. But sometimes like they design the laptop to be compact and they design it to be light, so they compromise with the cooling system, and that's why like even I have a very recent HP laptop, but I cannot operate it by putting it on my legs. It is still heating too much. I hope I answered your question. Thank you. Yeah. Yeah, basically they are compromising like what customer likes. Otherwise the same laptops can be cooled very efficiently, but it may be, yeah. Yes. Yeah, and as the temperature increases, its performance decreases. I think I have not shown that there is a graph. Yeah, its efficiency goes down, and over the time, its life goes down.
Another question, please. Thank you, sir. Thanks a lot.
Thank you so much.
Thank you so much, sir, for such an information and enlightening with your knowledge. I would like to invite our session chair, Dr. Nikhil Dev. I would like to invite our session chair, Dr. Nikhil Dev, to give a memento to our speaker, Dr. Afzal Hussain. Further, I would like to invite Professor Dr. Ravindra Kumar to present memento to our session chair, Dr. Nikhil Dev. Now moving on to our technical session. We, on the behalf of Department of Mechanical Engineering, welcome you to the third Biennial Information Conference on Future Learning Aspect of Mechanical Engineering, FLAMES 2022. Today, we have our honorable session guest, Dr. Nikhil Dev, Assistant Professor in Mechanical Engineering Department at YMCA University Science and Technology, Faridabad. He is having more than 15 years of teaching experience. He obtained his mechanical engineering degree from Punjab University, Chandigarh in 2005 and PhD from Delhi University in 2015. His areas of interest including combined cycle power plants, combustion and computational techniques. To his credit, he is having more than 60 papers published in reputed national and international journals. He has attended more than 50 FDP and STC at IIT and NIT and other prestigious institutes. Dr. Nikhil Dev is editor and reviewer of various national and international journals.
We also have Dr. Ravindra Kumar, is a professor of mechanical engineering at M&T University, Noida. He holds a bachelor degree in now we would like to invite paper ID 31 to present their presentation. 31.
How many others are here? Paper ID 166. 166. 187. Are you sitting in the right session? Yes, sir. May I approach you? Who is next?
Hello.
Now you can start, please.
Thank you, sir. Good afternoon, everyone. I welcome all of you to my presentation, which the title of the presentation is as the design of efficient quadrature scheme in finite element using deep learning. So the authors of this work is as follows: Rohan Chinskar, myself, Deepjyoti Nath, and Dr. Sachin Singh Gautam. The content of this presentation is as follows. The first, I will briefly give the introduction about the work and the finite element analysis and the artificial neural network which we have used, and then it will be followed by the methodology, results and discussion, conclusions, and the relevant references. So as we all know that the finite element analysis is basically a numerical technique which is used to solve the partial differential equation. The basic steps of finite element analysis involves the pre-processing, post-processing, pre-processing, processing, and the post-processing. So our work is basically focused on the processing part of the finite element analysis. In processing part, basically in the structural analysis, we compute the stiffness matrix and we solve for the primary variables. So in computing the stiffness matrix, we basically use Gauss quadrature scheme, which is an integration scheme. So we are basically try to optimize that Gauss quadrature scheme using artificial neural network. So the discretization of the equilibrium equation for a static structural problem leads to the following equation, which is where K is our stiffness matrix, U is the nodal displacement, and F is the nodal force vector. So the elemental stiffness matrix is of the following equation, which is where B represents the strain displacement matrix. D is your our material constitutive matrix. So to integrate the elemental stiffness matrix or any other elemental quantities in finite element analysis, we usually use Gauss quadrature scheme. So in the Gauss quadrature scheme, basically the integration is replaced with the weighted sum of the integrand prescribed. We basically evaluate the integrand at some prescribed point, which are called as a Gauss quadrature point, where we can see that xi is the Gauss quadrature point and wi is the respected or corresponding weight. So similarly, this the equation 1.4 is for one-dimensional integration, and for a surface integration and the volume integration also we can use the usual Gauss quadrature scheme. So coming to the discussion of how the Gauss quadrature scheme is implemented in finite element method is that basically we are focusing on how to optimize the Gauss quadrature scheme in calculating the stiffness matrix. So here these are the equation for the stiffness matrix for 2D and 3D analysis. So the motivation of the work is that in Gauss quadrature scheme, if the order of the polynomial is p, then we require minimum p plus 1/2 number of Gauss quadrature points. However, if we have a very highly distorted elements, there we require basically more number of Gauss quadrature points. Suppose in the minimum number of Gauss quadrature point for a perfect shaped element is suppose 6, then if it gets distorted during the loading condition, we require more number of Gauss quadrature point to integrate the element stiffness matrix. So the objective of our work is to how to get the optimum number of Gauss quadrature point to compute the stiffness matrix for a for an element. So as we all know that the machine learning field is also widely applied in various other fields, including science and engineering, healthcare, economics and all. So one of the very most popular machine learning algorithm is that artificial neural network. The artificial neural network basically mimics our human brain. So the building block of an artificial neural network we call it a neuron. So where we take the inputs input to the neuron, as we can see here in 1.2, that x1, x2, x3 are the inputs, and w1, w2, w are corresponding synaptic weights. We give we basically feed the weighted sum of this input and the synaptic weights to the neuron, and the activation function basically maps this inputs to the corresponding output of the neuron. So here are the various activation functions we use depending on our what type of problem we are solving. So this activation function generally changes. So this figure basically shows a schematic architecture of an artificial neural network, where we take the input as a first layer, and these inputs are passes through a sequence of hidden layers, and we get the predicted value of this network at the output layer. So in the next step, we basically compute the error between the whatever output we get from a neural network and whatever actual value we have, and we try to basically minimize this error using the gradient descent algorithm, and we continue to do that until we get the minimum error tolerance value, and the parameters of the neural network basically, which is corresponding to the synaptic weights, those are updated using the gradient descent algorithm. So coming to the relevant literature reviews, so here I am going to discuss only the literatures which says basically the application of machine learning in the field of finite element analysis only. So there is one work that is called a smart finite element, where it is directly predicting the nodal forces by taking the element state without computing the displacement field. So we all know that in the processing of the in solving the finite element method, we basically first compute the displacement field for structural analysis, then we compute the whatever elemental nodal forces are there. But in this work, they have directly taken the element state of the element, and directly they are computing the displacement field. Also, the Gauss quadrature the optimum Gauss quadrature scheme also been studied by Oishi and Yagawa. So they have basically in their model they also try to optimize the Gauss quadrature scheme, basically try to get the optimum number of Gauss quadrature points and Gauss quadrature points and weights. But however, in their model, their data are highly imbalanced. So to improve the model, we have also worked on to improve the accuracy of the model, then by data balancing. So coming to the stress prediction, we all know that the very highly when our finite element masses are very fine, last 5 minutes. Okay, sir. So then I will just skip this part, and then I'll move to the methodology then. Okay. So to get the data to develop the artificial neural network model, basically what we do is we change the nodal coordinate of the 8 nodal hexagonal element with this following relation. So here we can see the sum of the deformed elements. So basically we are trying to find out the corresponding what will be the optimum number of Gauss quadrature point for different shapes of the elements. So the basic the data generation procedure is as follows. We basically take the geometry of the element, we take the Young's modulus, and we take the Poisson's ratio, and we compute the stiffness matrix using some qth Gauss quadrature point. It varies from 1 to 9. Then we compute the error, and we say that the optimum number of Gauss quadrature point is q if we get an error of less than 10 to the power minus 3. So here we can see that in figure 2.3 that the training data distribution and the test data distribution. So training data are those data which we basically use to build our neural network model, and test data are those data which is not basically seen by the neural network model. We want to test the model and how basically it performs. So our ANN architecture is as follows. So we have the number of inputs as 20 number of inputs are there, where 18 inputs are corresponding to the nodal coordinates and 2 are the material property. We have 3 number of output neurons at the output layer, and we have 7 number of hidden layers. So these are the various activation functions we have used. So coming to the results and discussion, so as it can be seen from the table 3.1 that we have got very high training accuracy. But however, the testing accuracy for 5 Gauss quadrature point, it is very low. The reason is being that the data we have generated for this 5 Gauss quadrature point is very less. Due to the data imbalance, the model is not predicting for this particular Gauss quadrature point very well. So also the highlight of this work is that the accuracy of our model is better than the Oishi and Yagawa and Kashyap and others, the whatever model they have developed. So in 3.2 in this table 3.2, we can emphasize the fact that if suppose we require 4 number of Gauss quadrature point to calculate the stiffness matrix. Now suppose if we use 2 Gauss quadrature point, it gives the error of 11.758%. And if we keep on increasing the number of Gauss quadrature points, as you can see that the error value basically decreases. But as we keep on increasing the number of Gauss quadrature points, the computational cost will also increase parallelly. So we basically need to find out at what is the optimum number of Gauss quadrature point that we should use, so that our accuracy is within our prescribed limit or within our desired limit. So we have extended this work to a 20-noded hexahedral element. So earlier was from the earlier model. So here we have also got the very good training accuracy of 96.64%. But however, the test accuracy we still did not improve, and this is again due to the data imbalance problem. So here in figure 3.2 and 3.3, we can see there's some the training and testing results of the model that we have developed. So coming to the conclusion that we can see that the deep learning basically can be used for predicting the Gauss quadrature point for computing the stiffness matrix, which can significantly reduce the computational cost. Also, our model is basically capable of handling different kind of materials also. In the earlier works presented by the Oishi, Yagawa and Kashyap and others, they did not consider the variation of the material. They have only considered the variation of the shapes of the elements. So coming to the future work of this work, that this work can be extended to find out the optimum number of weights in the Gauss quadrature scheme also, because here we only did it for the finding out the number of Gauss quadrature point, but in the Gauss quadrature scheme there is a weight factor is also there, which is being multiplied with the integral. So this work can be extended to find out the optimal weights also, and we also can apply different machine learning algorithm to find out the optimal number of Gauss quadrature points. Here we have only tried with the artificial neural network. So here are the relevant references. So thank you. I thank you all.
Any question, please, from the audience?
Thank you for your
Yes, thank you.
My simple question is like, how do you test your model?
We basically in ANN, when we develop the model, we have some training data. For the training data, the model knows it's the correct output value. But when we test our model with test data, which the model do not basically see those data, we test on those data. Here I have shown that the test data also in one slide basically. Let me show you. Yeah, here you can see the figure 2. Okay.
So what are your criteria? Like any criteria that you think that your model is predicting good?
Yes, sir. We can see that basically we evaluate this is called a confusion matrix. Confusion matrix we evaluate. So you can see here. So I can explain it to you that, for example, this is a training result. So in this part, we see that the predicted number of Gauss quadrature point that is predicted by the artificial neural network model, and these are the required number of Gauss quadrature point. That's the true value, that which are actually required and which we get during the generation of the data that we know. So this pointer option is not working. Okay. Anyway, so if we see that how our model is performing well, that
So I understood your point. The second question is like, did you do coding for this, or you use some input code for this?
no, sir, we did all the coding by.
So did you compare with any other existing ANN?
No, sir, because
Because the ANN existing MATLAB and any other software also. So did you try to match the accuracy? Because you said that you did the coding, right?
So, so sir, I don't understand actually what. Sorry.
Like you did the coding for your LLM?
Sir, actually we developed this platform in TensorFlow. We did not do in a scratch. So TensorFlow basically is there. So we developed on the TensorFlow module.
You mean like Python?
Python, yes, Python.
You use the module already inbuilt module.
Yeah, inbuilt module is there in TensorFlow, which, but the basic challenge is how to get the optimal number of how many neurons you will use, how many number of hidden layers you will use, what will be your optimization algorithm. Those other things need to be studied.
You did not mention about like you did not acknowledge who did that original coding. What is the module basically? You did not mention anything about who did the original coding.
Sir, it's a collaborative work between. Okay.
What I'm saying is that Python, there are so many like modules.
Modules, yes, yes. I have to give the reference also. Yes, yes.
You did not know like which
Yes,
one
yes.
you did MATLAB or you did
Yes, yes.
INSys or you did Python, you did R.
Hmm,
You
hmm,
didn't
hmm.
know which one you were.
Yes, yes. I got it.
Thank you.
Okay. Thank you, sir.
Can you show me your first slide? What are the topic of your paper?
Okay. Thank you, sir.
Can I ask you a question?
Oh,
How
yes.
much time did it take for you to generate the data point?
Sir, it depends on how much data point we want to generate. In this coding, we have generated around 50,000 data points. So if we want to improve the accuracy, we can generate 1 lakh data point also, 3 lakh data point also. So I think it took around 6 to 7 hours for 50,000 data points.
I also want to ask you how you came to the 20 number. Why did you go between like you were showing me that like structure? How did you jump to 20 instead of any number between?
What 20?
You
Sir?
mentioned
Reference okay, so basically 20 is a very high number of Gauss quadrature point, and it is believed that if we keep on.
Do you have any reference to go to 20 or you just
No, sir, basically if we see the convergence of the error conversion up to suppose from 15 onwards, it does not deviate much, so we stop for 25 in that case. 20. So 20 is considered that it will give the most accurate value of the stiffness matrix. So we can go beyond 20 also, but that will not be much difference because we are anyway comparing with 3, 4 and 5 Gauss quadrature points. That's why. Okay.
Thank you. Now I would like to invite paper ID 166 to present their presentation.
You are supposed to sum up in
Yes, sir.
7 minutes.
Yes,
Then
yes.
we will be having 5-minute discussion.
Sure.
So good evening to all respected session chairs and professors and fellow presenters. Myself, Siddharth Pradeep, I'll be presenting paper ID 166. Title of our paper is Design and Manufacturing Process Related to Challenges of Additive Manufactured Parts, a review. So the authors are myself, Nitish Maharaj, Dr. Bhupendra Prakash Sharma, and my affiliation is with Amity Noida. So additive manufacturing is one of the most innovative approach in the advanced manufacturing techniques, and it has transformed the way we look at manufacturing and designing of equipments, products, and various other things. So it has changed our traditional view of subtracting from a base material to addition. Basically, we have reduced or minimalized the waste of materials, and we have incorporated technology and automation into the process. So designing being here is modeling or virtually sculpting the product to be made, and manufacturing here being transforming the raw material into the finished goods. As I've already said, the additive manufacturing has significantly reduced the wastage of materials. So the methodology adopted here is systematic review of paper, and we have incorporated papers after 2010, being that the technology has evolved over the period of time, and we have narrowed down to 26 papers included in the paper. And all the papers we have reviewed have topics related to the design, manufacturing of additive, related to additive manufacturing. So talking about literature review as it is, surface roughness was one of the most identified challenge, and it being that the occurrence of surface roughness was repeatedly found, and this has created irregularities, and the overall aesthetic of the component was reduced. And along with this surface roughness, residual stresses were also defect that was arised in research, and these residual stresses have caused variations in the overall manufacturing of the product and its overall functioning. So this is by when we look at the overall component, we'll have small build angles formed during the additive manufacturing. And these build angles are usually not very visible to an eye, but when we do SEM testing or under the microscope, we can see that there are small build angles. These build angles are usually due to the process parameters that is involved in the additive manufacturing, maybe the orientation of the print, the fill densities. All these can cause the formation of these build angles, and comes to the energy density and its influence on the flexural property. So as we all know that all the product made will be undergoing a different kind of stresses, and it has its own resistance. So the overall energy density is basically the concentration of the energy in the form of heat or any kind of resistance in the particular material. So all of these and all the flexural property, it is highly affecting because of the energy density. Now let's talk about the impact of heat treatment on these additive manufacturing parts. Even from the starting or the pre-treatment of the materials, even the bed that we use for the FDM manufacturing, we have temperature involved in it. And even after the production, we have it under temperature controlled areas. So even these temperatures actually matter to the manufacturing of the components and its final stresses and how the functioning and the performance of the parts goes by. And as we go on to this, all these challenges that we have identified here in effect control or affect the tensile property. Tensile property is nothing more than the Poisson's effect, and how the component is going to elongate, or how it's going to be reacting to the squeezing process. And with all these under the design perspective, if we go into the manufacturing perspective, we can see there is a stair steps that is a challenge. And these stair steps is mainly occurring due to the layer by layer manufacturing of the additive manufactured parts. So stair steps can be counteracted with the layer thickness. It all depends on what material we want, what product we want, the overall dimensions, and what type of machining we're using. So stair step is another defect that can reduce or increase the life of the product. And next we have the void formation. Void formation is a issue found mostly into the FDM method manufacturing technique, and this is due to the filling densities that we have vary. Usually for a FDM, for a locally produced good, we go from 25% to the 75%, and as the product, as we want to increase the product life, we go from 75 to as much as we can. So these actually control the voids in the product, and in large-scale manufacturing, we'll have time constraints, so sacrifices on the fill density is made. Then we have the limited material palette. So over the years, we have had different materials being introduced into the additive manufacturing field, and we have now have a wide variety of materials. But even these materials are still limited because we are not able to build particular material products that need more strength, or we need to bring more different properties. Another issue here is buildings. Yes, building scalability. Building scalability basically comes to the large-scale production, and it's personal fabrication techniques or like mass production. To sum up the literature review, we have separated these challenges into design process, that is surface roughness, residual stresses, formation of build angles, impact of energy density on flexural property, effect of notch load interaction on mechanical property, impact of heat treatment on additive manufacture part, effect of tensile property. And then the manufacturing, that is being stair steps, void formation, porosity, limited material palette, building scalability, personal fabrication, mass production, and rheological scaling of spherical powder dispersed in thermoplastics. To conclude, we need to solve these challenges in order to improve the additive manufacturing process and make it more accessible to industries, and gradually make them into large-scale mass production or large-scale production. And additive manufacturing is the future of manufacturing techniques in the large-scale industries. Thank you. And these are the references.
You did literature review.
Yes, sir.
What three top research gap you observed from your research?
So we have observed research gap from these challenges that more of it, most of the papers speak only few points. They have not discussed more in depth. We have taken the research further and gone into Promptly analysis, that's the MCDM analysis, to segregate these challenges and analyze how each challenges affect the process. And we have found that the FDM is one of the most flexible, or the challenges are very less for the FDM manufacturing, and we have done more research on that. So.
What other authors have discussed and what you found is need to be discussed?
So in most of the papers, so like few of the challenges are only solved. More are left unsolved. So these are the main challenges that has to be rectified to move into large-scale production of additive manufacturing.
I just want to ask a simple question.
Sure, sir.
Like when was that word additive manufacturing coined? Did you check? Like when that word came into existence, additive manufacturing? The first time they started using it.
I'm sorry, sir. I don't recall.
The term additive manufacturing, you mentioned, right?
Yes, sir.
So when was it coined? When was it named? Did you check?
Sorry,
because you
no, sir.
said that before 2010 there was no.
No, sir. Before 2010, sir, I have not included those papers.
Because that's why I'm asking.
Okay.
Did you check when that word additive manufacturing started? Because like nanotechnology, back in 2000, there was no word for nanotechnology.
Okay.
Machine learning, just 4-5 years back.
So we have found few papers related to 3D printing and additive manufacturing, like for 2009 and 2008 also. Yes, sir. Yeah. Sure, sir. So that's from my side. So any more questions?
I have 2 or 3 questions.
Sure, sir.
Go to the slide number 7.
Yes, sir.
Here you have taken this third bullet and fourth bullet.
Yes.
Both the names are same. Here they are also same.
Yes, sir.
Then how you will differentiate if I have go to the reference section,
Okay, sir.
then how you will differentiate because the author name is same and here is also same. So you have to put A or B also.
So they are from the same paper or they are different paper?
So third and fourth, sir, same paper, sir.
Then they should be in the same why you have to differentiate?
Sir, like I'm talking about that particular point, that's why, sir. I significant.
And like you have described here this from FDM. So have you mentioned anywhere what is FDM?
No, sir. So fused deposit machine, sir.
But it's mentioned anywhere.
Oh, sorry, sir. I'll improve.
Slide there were 1 or 2 spelling mistakes. You could go to that slide again. You will find it. Sometimes what happens, it is not necessary that this showroom is owned by the computer and they have not come by the computer, but that is not there because here it might misalignment. So you should take the random mistake.
Sure, sir. I'll improve next.
Thank you.
Thank you, sir.
Yes, thanks.
Now we will like to call 405, paper ID 405.
Please stay with the time limit. 7 minutes plus 5 minutes.
So good evening everyone. My name is Gunjan Taneja. I am here to present my paper on the topic Design and Simulation of PV Solar Cell System with Microgrid and Fuel Cell using Discrete PID and Fuzzy Controller. The authors included are myself, Dr. Vijay Kumar Tyal and Mr. Kamlesh Pandey. I have under the affiliation of MIT University, Uttar Pradesh, Noida. So these are the contents I have included in the presentation. I will be discussing about the objective, introduction, literature review, proposed work, simulating model control schemes, followed by the result, conclusion and the references. These are my 4 basic objectives. I have aimed to design and simulate a model of solar PV module with fuel cell and microgrid, development of simulating model of solar PV fuel cell and microgrid integrated system with the help of the fuzzy logic controller. The third objective is development of simulating model of solar PV fuel cell and microgrid integrated system with discrete PID controller and comparison of different control scheme for integrated system. So this is the introduction. I will be discussing about the photovoltaic system. The scientists refer to the solar cell system as photovoltaic cell because sunlight is converted directly here into the electricity. There are the 4 steps in the working of the solar PV cell. The solar panel converts the energy of the photons into electricity. This process is called as the photovoltaic effect. When a photon hits the photovoltaic device, its energy is transferred from the photon to the local electrons in the material. These excited electrons begin to flow, producing an electric current. Solar cell then produce the DC electricity, which is typically converted to the AC with the help of the inverter. This allows it to send back to the electric grid, which operates with the AC electricity as well as the power appliances in the customer's home. The other two components I have used in my project are the fuel cell and the microgrid. The fuel cell basically works simply. It is composed of an anode, cathode and an electrolyte membrane. A typical fuel cell works by passing hydrogen through the anode of a fuel cell and the oxygen through the cathode. At the anode side, a catalyst split the hydrogen molecules into electrons and the protons. The process of the electrolysis takes place, followed by the microgrid. The microgrid is basically a tiny modular and decentralized power generation and distribution system. The major feature included in the microgrid is that it can work in both island mode as well as in the grid connected mode. It acts as a controlling element. Basically, it is a clean resource, that's why it is nowadays used. So this is the literature review I have included in my work. The basic literature that is I will be discussing about is the balancing of the frequency of the load by PID tuning, that is developed by the Nayak et al. And this is the latest work that is being done, followed by the fuzzy logic controllers that are used for the MPPT controlling of the fuel cell. So my proposed work acts as follows. The proposed work includes the design and simulation of the PV array with the fuel cell and the microgrid. Modeling is completed with the help of the MATLAB software. The power management is done with the help of the battery. To achieve the best result, discrete PID controller is compared along with the fuzzy controller. A modified fuzzy logic controller is used in my system, in which the width of the membership function is increased to get the desired response. Mamdani type fuzzy logic controller I have involved. So this is basically my Simulink model. My Simulink model consists of the two components. First is the PV array, followed by the two fuel cell. The specifications of my modules are given on the left hand side. In the PV array, it is basically of type First Solar FS272. Its voltage is 96 volts and its power is 1 kilowatt. Series connected modules are 2 and parallel connected modules are 10. And the number of cells connected per module is 116. The two fuel cells I have involved in this work is basically of the power 2.5 kilowatt and voltage as 48 volts respectively. These three devices are connected in parallel with each other. Then they are connected with the help of the battery. That involves the power management function. The battery is then connected to the inverter, and then it is further connected to the universal 3-bridge system. And then there on the right hand side there are the loads that are connected. There are two types of the load I have involved in this work. They are basically the RL loads that I have used. One is of the 8000 watt and the other is of the 10,000 watt that I have involved. In this type of the model I have basically used two types of the controller. First one is the discrete PID controller that I have involved, and the second one is the fuzzy logic controller for checking up the control systems. So discussing about the control schemes, there are two control methods. First one is the discrete PID controller. The design of the system employs a discrete PID controller. It is mostly widely used controller in industries. It has a faster response time as compared to the normal PID controller. In this system, Kp is considered to be 1, Ki to be 1, Kd to be 5 and filter coefficient is considered to be 100. The selection of the parameter is done on the basis of the trial method. The second type of the controller I have involved in this work is fuzzy logic controller. Basically, I have used a modified fuzzy logic controller. In this, the width of the membership function is increased to give the desired result. The input and output values are defined using the following variables: NB negative big, NM negative medium, NS negative small, ZE as 0 and PS positive small, PM positive medium and PB positive big. For comparison purpose, 3-phase bus voltage and current waveforms, load voltage and AC source voltage are considered. Shifting towards the fuzzy logic controllers, the figure 1 here represents the block diagram of the fuzzy logic controller. I have basically defined the 49 rules that I have used for the fuzzy logic controller. The figure 2 represents the fuzzy rules that I have used for my work. And the figure 3 here represents the modified fuzzy membership function. The difference between the membership function I have used and the work that is already done is that I have used a modified fuzzy logic controller in which the width of the system is increased. That gives the better response. Now shifting towards the simulation results I am getting. Yes, sir. These are the results I am getting with the help of the discrete PID controller. The figure 4 represents the 3-phase bus VI measurement using discrete PID controller. As in the figure 5 and figure 6, we can see that there are distortion in the waveforms. While comparing to the results of the modified fuzzy logic controller as in figure 8 and figure number 12, we can see that there is no distortion in the waveforms. So that's why I can say that modified fuzzy logic controller is better in response as compared to the discrete PID controller. Shifting towards the load voltage parameters that I've obtained, we can see that in the overshoot, discrete PID gives comparatively more overshoot as compared to the modified fuzzy controller. So here the conclusion of my work is that in this work the design of PV array system is integrated with fuel cell and microgrid is carried out. Further, for the AC source voltage, the fuzzy controller gives less overshoot as I've shown in the table, whereas discrete PID controller lead to the unstable system because of a very high overshoot. The overshoot obtained for the load voltage waveform is reduced from 45.9% to 28.9% by using a fuzzy controller. Thus, I can conclude that a modified fuzzy logic controller is far superior compared to the discrete PID controller for the proposed renewable energy system. So these are the basic references I've used for my work. Thank you.
Questions, please.
Yeah, I have a question. You have used R as for the load.
Yes, sir.
So what is the use of using inductor here? You can just the resistance. Why are you putting the L?
Sir, but on considering just the resistance, my AC load was not getting correct value. I have tried for R load as well. I have done the comparison, but my AC load was showing the error because I was trying to get the values in such a way that from the DC side and the AC side, I am getting the my system is stable. But on considering the R load, my system turns out to be unstable. That's why I considered of RL only.
Okay, second thing is that whenever you are connecting the fuel cell with the solar photovoltaic cell, with the fuel cell you are getting the lesser voltage with the that was nearly 48 volts.
Yes, sir.
And with the solar panel photovoltaic
96
you are
volts.
96 volts.
Yes, sir. That's why I've connected two fuel cell in parallel. Two fuel cells were connected in series along with the PV array. It was connected in parallel. So two fuel cells of 48 volt each I've connected. So they were together giving the 96 volts, and the above one PV array was of 96 volts.
So whenever you have to run the fuel cell, you need the hydrogen. How do you get the hydrogen for the fuel cell?
Sorry, sir. I know.
When we are using DG cells, the fluctuations in the power generation, so did you include these fluctuations to
Sir, I have just done with the help of the MATLAB module only. I have not used any real-time data. So in the module I have used the fixed value. I have not used as I have not told. I have considered irradiation to be 1000 only. I have not shown any variation from the source side. If I would have considered that, then obviously my power voltage and power curves would be changing.
perhaps there will be more ways to provide
Yes.
provide the consumer from the DG cells as some real data.
Yes, sir.
Is there any specification you have selected MATLAB?
Sir, actually I am working from using MATLAB for past 2 years, so I'm quite good in it, so that's why.
Thank you.
Okay. Thank you, sir.
Paper ID 40.
So good afternoon, sorry, good evening. My name is Dr. Rahul Gupta. I am working with MIT Business School basically. So actually this conference is for engineers, but I have tried to assimilate few newer artificial intelligence and its applications in our marketing field. Since we deal in the management and marketing is my core area. So with two of my colleagues, I have tried to put in something. Let's see if I am able to justify this. There's a professor in marketing, Professor J. McCarthy from Stanford University. He established artificial intelligence way back many years before, and little it knew about artificial intelligence. We find its use in multiple areas of science, medicine, automation, games, and now in our marketing area. Artificial intelligence with deep learning or machine learning enables computers to learn by themselves regarding consumer behavior and buying behavior. So one example, if I'll take it here, so when we go to shopping in a retail store, so they have put up so many cameras and all so that they are able to trace our eyeballs, and ultimately this same information can be passed on to the manufacturers that on which part of the product or in which area of the store consumers are actually spending their time. So innovations leads to success, electricity, steam engine, these are the few examples where we have grown up from the older technology to the newer technology. So technological innovations like hardware, software, processing tools have enhanced performance in various management domains like marketing science, which we are dealing in. So IoT, cloud computing, big data, data science, blockchain, and AI are the new technologies which are creating winners and losers across many industries, and our marketing is certainly getting a lot of advantages from there. So in the McKinsey's report, AI adoption backs a global profit pool for 1 trillion by 2030, where few scientists have said that capabilities and makes them free from unproductive and repeated tasks. Like I was just talking about the retail store where a lot of manual things were being performed earlier, but now with the help of these new technologies, a lot of things are being performed by machines. Say for example, collecting the shoppers' data, passing on to their suppliers, looking back at what all those items which we are buying. All of us are buying a lot of items from Amazon and Flipkart, and we find that whatever items we have purchased in past, automatically we get that from your last order was containing this. So all those things they are doing with the help of these new technological tools which they are implementing in the system. AI, I will not go into this, like no way to define what actually AI is, but as per the theory and development of computer system able to perform tasks normally requiring human intelligence, such as virtual perception, speech recognition, decision making, and translation between the languages. So all these things are automatically being performed by these new technological tools, which are helping the manufacturers and the retailers also, and we in the marketing field are getting a lot of benefits out of that. Few developments in the field to adopt some of the other technologies: advanced computing, cloud-grade computing, transparency through code sharing, Bitbucket, GitHub, GitLab. Being in management, I really don't know what all these technologies are or how these work. I only have read about their implementation, that how these can be useful for us. And various open source softwares are leading to advancements. Many fields like healthcare, automobile, finance, monitoring environment, agribusiness, sports, energy, conservation, etc. have enormous use of AI and enhance human life and work. In areas like engineering and IT, analytics are participating AI for quite some time, but now the area of management and marketing also started using AI and getting a lot of benefits. Data of market analysis, customer insights, and competitive intelligence from various channels of distribution and communication are analyzed, and strategies are formed with predictable results. So the retailers like Amazon, they have been tracking our data, and their coding and all those technological advancements are helping them in predicting that in the next season or in the next purchase order, these customers are going to give us what all orders. So that from the back-end side, when they are planning for their supply chain and the procurement from various sources, they are very easily able to manage it. Because normally when you talk about a retailer, he used to keep a few thousand stock keeping units. But when we come on to these online retailers, they are having lakhs and lakhs of stock keeping units with them. And if we look back into from supply chain perspective, managing all these items is a very difficult task, and all these types of technologies are certainly helping them that how much they should procure and from where and how they should procure. One study by Mazurek studied that IT services naturally benefited marketing science. IT and marketing both became a natural allies and achieved synergy. It becomes important to study and understand AI and its available tools and their applications in marketing. So the objective was to most exciting for innovations where technological advancements are happening with lightning speed, virtual conferences, robotics, self-driving cars, smart equipment at home, and smart healthcare service monitoring patients in hospitals, and online gaming, chess and Go, and few technological innovations under AI and deep learning.
Professor Emeritus J. McCarthy from CS Departments of Stanford University established AI as a field in 1956 during the Dartmouth Conference at Dartmouth College, Hanover. McCarthy in 2006 and predicted an intelligent system as a good human order. Firshin and Coles in 1973 hypothesized various products that would be supported by AI in the next few decades, and many will become has actually become a reality in nowadays. Grunrus, he's a marketing professor, said delivering value to customers is a critical aspect of marketing. That value may be goods, service, ideas, information, or a solution to a customer's requirement. Bennett said that the E.J. McCarthy conceptualizes marketing mix 4P. Actually, this McCarthy's 4P, like maybe from some marketing area I can say one line, the product, place and price, promotion, which was being given by this gentleman way back, and then later people, the professor started building upon the marketing concepts on these 4Ps. And from where these 4Ps have been drawn, a concept taken from the Borden's, one of the another professor, 12 fundamental mixes of marketing. I'm not going to read them. So our goal is to find the opportunity in AI applications marketing area and study the two questions. In all areas of AI are applied in marketing, and find out the implications of AIT for marketing practitioners. These are the few examples, like voice processing. We have been using Alexa, Siri, Google Home. Text processing, Alpine helps in a walking guide in a shopping center, a mobile app for banking services, ATMs, or purchasing bank products. Image recognition, KFC uses face recognition to make payments. Shishidio app suggests face screen after analyzing photo and wealthier condition. eBay supports the search of an item online by a photo. So all these few uses are there. This is the product, place, price and promotion, the four basic marketing mix, and how artificial intelligence is being utilized in that. Choice making, Plum offers a separate saving plan and suggests a per account balance and financial capabilities. Spoofify offers destination machine travelers a music preference. Daigo, a chatbot that helps in preparing a cocktail recipe using mobile data and app. Montadla suggests UV protection filters also. Okay. So some other uses in marketing. Right. So numerous marketing areas are benefiting from using AI applications. 5 areas of AI which gives benefits are text recognition, image recognition, voice recognition, vehicle routing, and the data which goes back to the processor and come back, like in the case of self-driven cars, and autonomous robots. Support commercial solutions with AI applications. Marketing through text recognition, image recognition, and voice recognition gets extensive applications in the marketing area in various technological companies like Amazon, Google, Apple, and Microsoft. Autonomous robots and autonomous vehicles are infrequently used as marketing tool, but find their applications in industrial management distribution. So actually it was from the management area, but I find it relevant to have it in a conference in an engineering background so that I may be able to do the justice.
So I have one question.
Please.
Please do some case study so that we can see the practical difference what the AI is creating in the market.
Certainly I would like to be there in this and will do this. So nice of you. Thank you very much.
Next paper ID 540.
Good evening, everyone.
We have 7 minutes to complete your...
Sure, sir. The title of my presentation is Modeling of SPWM in Technique-Based Three-Phase Inverter and Boost Converter for Photovoltaic-Based Water Pumping System. The authors are myself, Dr. Pallavi, and Dr. Ruchira. This is the outline of my presentation. So the availability of water is a challenge during the warm summer months, which is one reason why agricultural production is so dependent on water pumping system. PV cells are able to harvest solar energy and transform it into usable power during the summer months because electricity can be unreliable in more remote and rural places. We have switched to using solar water pumps. Pumps that are driven by solar panels both save energy and cut down on carbon dioxide emissions. Inverters are used for photovoltaic systems that generate power in the form of alternating current. It takes the direct current power output from solar arrays or wind turbines and converts it into clean alternating current power so that it may be used with appliances that require alternating current. Many high voltage applications necessitate the use of three-phase inverters. The main challenge in inverter designing is reducing harmonic distortions to improve inverting performance. Typically, SPWM is widely used to activate the inverting switches and control the overall harmonic distortion performance of the inverter. This paper makes two contributions. First, an improved SPWM modulation is generated for designing a three-phase voltage source inverter. THD is then evaluated using VI measurement in the second pass under various load conditions. THD exists in the system as a result of the use of switches. This is the figure 1 shows the block diagram of PV-based water pumping system in which we have a PV array, boost converter, an SPWM three-phase inverter, a motor, and a pump. An induction motor drives a centrifugal pump that is linked to its shaft. To achieve maximum power, the frequency is modified using the incremental conductance MPPT method. The output of the power electronic converter is routed into the induction motor and a centrifugal water pump is coupled to the induction motor shaft to operate as a load. Power electronic converters such as boost converters and SPWM inverters deliver the best conceivable output to the induction motor. Some criteria is taken into account for the system, such as the pumping level is 50 meter, vertical rise is 3 meter, friction loss is 10.9. The average number of peak sunlight hours are 5 hours in India. The amount of water to be pumped is 90 meter cube per day. To implement the simulation model, all the modules are to be designed in MATLAB Simulink. Figure 2 shows the Simulink model of a boost converter. The traditional boost converter might be utilized in a variety of power electronic applications, such as regulated DC power supply and solar PV system. Its job is to increase a low DC input voltage to a greater DC output voltage of a desired load. The converter operates in two current modes, discontinuous current mode and continuous current mode. Figure 2 depicts the simulation model of a DC to DC conventional boost converter. When the switch is turned on, the diode reverse biases, isolating the load stage. The inductor stores energy from the input source. When the power switch is turned off, the load stage receives energy from both the inductor and the source. Thus, the load voltage is larger than the source voltage. The downsides of typical boost converters are high ripple current on active and passive components, high voltage stress for power switches, and need for a large capacitor value to maintain a constant output voltage. Next, we will discuss about SPWM switching technique. It is a method that employs two types of waveforms, a reference waveform and a carrier waveform. The reference waveform has a fundamental frequency and is sinusoidal, while the carrier waveform has a high frequency and is triangular. The frequency of the carrier waveform determines the inverter switching frequency. As the carrier frequency rises, so does the switching frequency, and the frequency of the inverter output is determined by the frequency of the reference waveform. Comparing the carrier waveform outputs to the reference waveform outputs yields the output frequency. The modulation index can be used to adjust the fundamental frequency component of the output voltage. A three-phase SPWM inverter. The inverter, which is designed for 5.5 kilowatt motor. The rating of the inverter is 4.4 volt amperes and designed for 780 volt DC input. The pulse width modulation of each set of MOSFETs is determined by comparing each of the three sinusoidal waves to the triangular wave, and this is known as sinusoidal pulse width modulation. This is the application of power electronic converter in PV based water pumping system. The PV system is composed of 10 modules connected in series and 4 modules connected in parallel, with 6 solar cells in series for a total output voltage of 43.2 volts. Each solar cell has 7.34 amperes of short circuit current and 0.6 volts of open circuit current. The figure utilized for solar irradiance is 1000 watts per square meter, and the system may generate up to 2000 watts of power. The MPPT system makes use of the incremental conductance algorithm. Before computing the output power, this approach logs the immediate voltage and the current readings. So the load output voltage is 780 volts with a fixed DC input voltage of 400 volts. The predicted values of the inductor, capacitor, and load resistance and proper selection of the voltage and current ripple factor. Consequently, the step-up converter will increase the DC voltage. The simulation's result shows the fundamental voltage and total harmonic distortion while using a filter for SPWM with MA1 and carrier frequency 5 kHz amplitude modulation ratios. The simulated fundamental voltage of the SPWM inverter has a THD of 2.24% as shown in the figure. As we can see, the THD for SPWM inverter here is 2.24%. So I will conclude by saying that the primary purpose of a boost converter is to raise the voltage from a lower fixed value to a higher one, and this allows the boost converter to be utilized for applications involving solar systems that are either independent or grid connected. An inverter is required in a grid system for the purpose of converting direct current to alternating current. On the other hand, for the sake of this investigation, the fundamental circuit was utilized in order to keep the system's overall complexity to a minimum. The proposed work intends to create a control circuit, an inverter circuit, and a boost converter circuit as a part of a complete switching strategy for inverter applications. Simulated and analyzed variables include total harmonic distortion, voltage, control circuit output waveform, inverter circuit, and a boost converter circuit. According to the investigation, the inverter has a THD of 2.24%, which is within the IEEE requirements. These are the references. Thank you.
Dr. Palvi, I am not confused about can you go a slide which is before the conclusion, result simulation?
Yes,
before that. Before that. And one more. Yeah. In this, you are using this system may generate up to 200 watts of voltage. Is 200 watts of active power.
Yes, sir, it is.
Like that, earlier also you were mentioning this is 43.2 ampere, 0.06 ampere. Is it ampere or volt?
It is volts, sir. 0.6 volts of open circuit voltage.
When you were mentioned like ampere.
Okay.
And how you will measure this short circuit current, 7.3 volts?
So actually we are using a that model is available in the MATLAB only. So
that's available, but it will be shown. How you will measure this? It is also that assumptions also I am having some doubts. Can go to assumption part.
which one, sir?
Yeah, this one. You are trying to lift the amount of water that is only 90 meter cube.
Yes.
Then what will you do with this that little amount of water per day?
So actually these values are taken from the base paper which I have considered.
So they must have given some utilization of that. That one not here. They are just
So
I think you should take care of this thing.
okay, sir.
That you must put something that how we can use it. If you are going to take 90 meter cube, I think they must have some justification regarding to the specific work, specific work they are using.
Okay, sir.
Any other one? Any other question? Thank you.
Thank you. Thank you, sir.
There are some basic suggestions. Your font size is too small for a PPT. content is too large.
Okay. Sir, I'll try to improve that. Thank you, sir.
Who is next?
Now I would like to invite paper ID 187 to present their presentation.
Hold up. Yeah. Oh yeah, sure. Sure. So good evening, respected chairs and colleagues. As though there's not many of you, but I'm still really glad to present. I would like to begin by saying I was very inspired by all of the faculty's presentations, and I would like to begin by saying that the title of our research paper is Modeling of Kinematic Chains and Mechanisms, with special emphasis on multi-link jointed chains mechanisms. Today, the presenters will be Ojasvi Rajiv Sharma, my good friend and colleague, and myself, Shaurya Bhatnagar. So, as you can see here, we have the introduction. I'm sorry, Ojasvi, can I just? Yeah, we have the introduction, the literature review, problem formulation, methodology, results and discussion, conclusion, and references. So, I would like to begin by saying that you can obviously read the points here, but I would like to begin by saying that we were focusing on kinematic chains as a crucial part of any machinery, of course. With the advancements in technology, as you can see here, the structure of kinematic chains has also become more complex. I would like to just give you a giveaway here that we are focusing on 8-link kinematic chains because we want to give rise to better usability and more precise movements in chains. Now, the higher the number of links in a kinematic chain, higher the accuracy and the movability. And I want to quote an example here by saying that we could also consider surgery as a very important example here. And higher the accuracy and higher the number of links, the higher the precision we will have in robotic surgery, which is one of the examples. Now, modeling of kinematic chains in a way that we realize is true, is in its true potential is of utmost importance. I would like to invite Ojasvi to talk about the literature review.
So during this literature review, we basically went through a lot of research papers which were done by a lot of very learned people. Now, what you will see is that what we are trying to do over here is detect isomorphism in kinematic chains, because you may see that a chain might be 8-link, but there are various different structures in which those 8 links can be construed together. And that is the thing that we are trying to discover over here. That is the thing that we're trying to focus on over here, because way in which kinematic chain works is that you might find the same movability, but the structure can be different every single time. The way in which the limits of that kinematic chain can be construed are going to be same, but the way it is structured is different. That is what is beautiful about a kinematic chain in general. So there were a lot of ways in which isomorphism could be detected. And in our literature review, we found out that there were ways like joint-joint matrix. There were ways like Mackay's algorithm. There were ways like topological graphs. But the thing that we found about all those approaches were that they were way too complex for even a normal student to get into. and we found out that those approaches required a study of their own, and at the same time they were very precise, up to 5-link kinematic chains, mainly 4-link kinematic chains. Yes, topological graph in general was very accurate till 30-link kinematic chains, but we found that 30-link kinematic chains were like hardly ever used, because a requirement for that particular number of chains, that particular number of links was not there. It was not existing up until this point in time. So we wanted to find out a way in which we could detect isomorphism in a more feasible manner, in a more efficient manner. So further we went on to the problem formulation, how we came up to this. So please start.
So, as you can see, our objective was to formulate a technique to detect, as Ojasvi mentioned right now, to detect isomorphism in kinematic chains, which was viable for higher linked kinematic chains, as we worked on 8-link kinematic chains. And it was more efficient as compared to the other approaches out there. So there are, as you may know, there's a lot of techniques to detect isomorphism in kinematic chains. But it starts losing, those methods themselves start losing accuracy after 5-link kinematic chains. The techniques used for higher link kinematic chains, the other techniques that are used for higher link kinematic chains are very complex and inefficient. Right, I would like to invite Adasvi to talk about the methodology here.
So for this particular thing, what we decided to do was we decided to apply the polynomial approach. Now for this, we decided to build everything from scratch. So this is one of the 16 base kinematic chains that we designed. Now, designing a kinematic chain in itself is a very, very complex task. So we made sure that it would suffice with the Grobler's equation, and it would also meet the Grashoff's criterion, which is basically that the longest link and the shortest link should be equal to or less than equal to the other links, the sum of the other links which are present there. So based on that particular theory, we designed an 8-link kinematic chain, and we decided to do our research and our analysis on that. So the case study has been built around that. Now we have taken this particular chain that you can see on the screen as our main case study because of constraints of time. So we could work on only one. You can see that there are 4 ternary links over here. Now to do any kind of research on kinematic chains, to do any kind of solutions on kinematic chains, what you need to do is that you need to convert the ternary or the quaternary links into binary links. That is the first and foremost step when you're applying a polynomial approach that we did. So this is what we've told, that initially the binary links were ignored because they were already there. We don't need to do anything with the binary links. We need to straight up work on the ternary links. So that is what we did. Now the ternary links were converted into binary links separately, one by one link at a time, using the formula of NCR. Now what that does is that it converts one ternary link into a binary link one at a time, and that particular thing gives us different invariants of the kinematic chain in itself. So as you can see, our base kinematic chain is here on the left hand side, and on the right hand side you can see what happens when we convert one ternary link into a binary link one by one. So if you see over here 1 of 1, 2 of 1, 3 of 1, and 4 of 1, that happens when we convert just one ternary link into a binary link. And similarly, we get different variants by converting one of those ternary links into binary links. That is how we got 15 invariants of just one base chain. And what we did afterwards was that we calculated the joint values of the same. Calculation of joint values is something that we did on MATLAB, and we further applied the poly function which is available on MATLAB for the same. Now what that does is that after you get the joint values, so once you get the joint values, you get the base joint values which are like absolute. It is when every single link is free. It is not stationary at all. That is when you get all the absolute values. Now what you do when you apply the poly function is that you start fixing links one by one. So in this particular case, we took an 8-link kinematic chain. So we started fixing one link after another, and we got different polynomial coefficients. That is the research that we did, and Shauri will explain to you what we got as a result.
So as you can see here, right here, I'm going to move my cursor here. So these are the base coefficient values, which is basically without fixing any links. They're all random here. But as we fixed all these links, you can see that there's 1, 2, 3, 4, 5, 6, 7, 8 links, since we're working on 8-link kinematic chains here. So we fixed the first link, the second link, the third, the fourth, the fifth, the sixth, the seventh, the eighth, and we got different polynomial coefficients for each one right here. And in the second example, as you can see, we have the FL, which is the fixed link value, and then we have the EL. And what this basically entails here is that we fixed the first link, and then we fixed the second link, and we got the same polynomial coefficients, right? And this gives us 5 different combinations right here. Because for the first one and the second one, we got the same polynomial coefficients and so on. That's basically what that entails.
Yes, sir. So we finally come down to the conclusion. And as for the conclusion, we get to know that the polynomial coefficients that we obtained were different for the equivalent the mechanisms that we made, but they were different for the distinct mechanisms. That is when we started fixing the links. At the same time, we also want to tell you that this particular approach did not consider the combination of kinematic pairs or like joints being like pin joints or any other different type of joints. We considered and we focus mainly on the simple joints. So that is one of the areas that we did not further progress into. And at the same time, this approach was implemented for multiple chains because that is what we wanted to focus on, because most of the approaches that are out there are right now only specified to like 4 links, and that is something that we wanted to change because right now with the advancement in technology, you require more links, you require better movement, you require more precision. And we wanted a very feasible, a less time consuming and a more efficient way in order to achieve that particular thing. So this is one of the ways that we approach this particular problem. At the same time, at the end, you can see these were our references. There are more in the paper that we have. For now, this is it. This is it from Shore and my side. We are open for questions.
Thank you so much for your time.
Thank you.
What is the use of degree of freedom in your analysis?
So that is a very good question. Number one, sir, what we've done is that the degree of freedom with this particular chain that we have taken into consideration is 1. So the thing is that when you make a kinematic chain in general, right, you have to follow the Grashoff's criterion. Now what the Grashoff's criterion and what the Grubler's criterion says is that when you make a kinematic chain, you need to make sure that the degree of freedom is 1 when you are using simple joints. That is the criterion that you must follow when you're making kinematic chain. Otherwise, that kinematic chain itself is not sufficient. It is just invalid. So that is what we focused on. And the degree of freedom in each and every chain, in each and every invariant is 1. Whether you fix one link or whether you use ternary links or anything, we made sure that the degree of freedom was 1. That was something that we had to do as a compulsory thing because we needed to make sure that the kinematic chain in itself was viable and we could work on it.
Can you show this some examples that I'm showing you?
So, sir, this is the kinematic chain that we use. Now, sir, over here, the degree of freedom is 1. Now, what we did was we analyzed the entire chain on its own. So, sir, what we did was that we first of all made sure that there were no more than, there was a maximum of ternary links and no quaternary links, which was very important because quaternary links in itself, they take a much higher time to analyze, and at the same time they require double the effort in order to like turn them into like binary links. And at the same time, you can see that all the ternary links which are present over here are well within the specifications of the Grubler's and the Grashoff's criterion. Now, if I am to like explain it to you, what the Grubler's criterion means over here is that according to Grubler's criterion, the degree of freedom that we need to have is 1. So what we did was we took 4 links in total. And after taking 4 links, we applied the Grashoff's criterion. What the Grashoff's criterion says is that the smallest link and the largest link, the sum should be equal to or less than the other links which are present over here. So this would be the smallest link over here, this would be the largest link. This sum should be less than or equal to the sum of these two. Only then is the kinematic chain viable. So just like this, we made pairs of 4-linked kinematic chains into an 8-link kinematic chain, because that is how you would make a kinematic chain that is more than 4 links and make sure that it is viable. So that is what we did overall. And we came down to this particular kinematic chain. Now, I would also say that we made further more kinematic chains, but the problem was that there was a time constraint that we had. So we worked on this. Now, while working on this, since there are like 1, 2, 3, and 4 ternary links, right? So whenever you're calculating anything which is related to kinematic chains, you need to make sure that every link is a binary link. So we can't have ternary links. So we converted one link into a binary link. We got 4 different invariants. We converted this one along with this. We got 4 more. So just like that, we got 15 invariants of the same chain. And then we applied the polynomial approach on this particular chain. And we found out that this was more efficient, this was less time consuming, and this was something that even a normal student could actually do without applying much effort to it, which was something that we devised on our own. So this was something that we did. Okay. Thank you. Thank you so much.
Thank you for your time, sir.
Thank you. Now I would like to invite paper number 16 to present their presentation.
You are not taking it? File you are not taking? Presentation.
So this is your folder. You can present.
No, you just copy the one first one.
So I just copy and do that. Okay. So just
okay, that's fine. Okay. Ladies and gentlemen, including session chair, I am going to, this is Swapn Purwa from NIT Durgapur. I am going to present this paper, Computation of Shape and Departure of a Non-Spherical Bubble in Nucleate Boil. Yeah, that's fine. And my co-author is Jyoti Bhatti. Now, this non-spherical bubble or bubble shape change when it is boiling, particularly in the superheated surface or heated surface, shape of the bubble always changes. And this is the essential part of the bubble dynamics, like when bubble growing or bubble collapsing or bubble departing from the heated surface. And this collapsing, this kind of bubble dynamics feature is very much applicable in the maybe that in nuclear industry and metal industry, and it is determining the interfacial heat transfer. Large amount of heat transfer it is determining. At the same time, what I am trying to say, and since there is a large amount of heat transfer required, we have to go by evaporation. Normally we do that, which is exercised in the nuclear industry and metal industry. As you see that, and you can see that shape, bubble shape, when it is growing or collapsing, bubble shape is basically that it is changing the drag force. It is changing the drag force or drag coefficient when bubble is moving, and the bubble shape is there. And at the same time, you see that that rise and deformation of bubble and drops. It is dictated by the non-spherical shape. And there have been a lot of studies essentially have been done by assuming the spherical bubble, but non-spherical bubble is considering non-spherical bubble is less studies there. As you see that spherical bubble growing at the heated surface, and here there is a mode of bubble collapse and a mode of bubble formation. There is one mode A and mode B. And you see that when that apparent contact angle or instantaneous contact angle is higher than the your equilibrium contact angle, then it is called the mode A bubble formation. At the same time, when the instantaneous contact angle is higher than the contact angle equal to the equilibrium contact angle, it is called the mode B bubble formation. And we later saw that the deformation of bubble is dictating the shape of the bubble when it is growing. That the deformation takes place, and it becomes when deformation takes place by the drag of the liquid, then it changes from the spherical to non-spherical bubble. And you see that there are a couple of authors have already done that, assuming the non-spherical bubble profile, like ellipsoid or spheroid or polar, what is that? Now there is a general concept to shape the bubble by using the capillary equation. But here we have extended the capillary equations where that non-spherical bubble can be shaped. That we see by the drag force, and we have modified the equations by including that growth force by replacing that dynamic pressure difference term in the capillary equation, which is called the Young modulus equation. And you see that obviously we have compared this result with that, but eventually you have seen that this capillary equation or Young-Laplace equation is not quite useful in shaping the non-spherical bubble. So we have done some other way. For large non-spherical bubble, what we have done, we have modeled the deformation, modeled the bubble deformation, then we have shaped the bubble. Obviously we have assumed some amount of some bubble profile, whether it will be spheroid or ellipsoid or what is called that, and it is done at the high super 8. And we have compared it with some CFD data also. This is the mathematical formulation of that Young-Laplace equation, which is basically the force balance equation, pressure difference across the interface, which is balanced by the surface force, hydrostatic force, and the dynamic pressure force. That equation is quite available in the literature. I am not going to describe all this in details. In the figure 1, you can see that schematic. And here we have solved this ordinary differential equation by Runge-Kutta method to find out the shape. This ultimately the second order Runge-Kutta method we have found by solve that, and by putting the dx ds and dy ds is equal to sin phi and cos phi. Cos phi and sin phi is the angle that we show in the figure 1. And at the same time, what we have done, when I am solving that, this equation, it goes certain value of x, then it becomes unstable. Then we do backward problem that we start with the inverse problem, which is called the dx2, d2x, dy2. We transform that equation to the form of the inverse form, which is called the x, which is the function of gx. And that we have solved with the initial condition or boundary condition x0 and gradient 1. That is for the spherical bubble. And what we have done next, that we have one problem is there. When you are doing this shape, spherical bubble or non-spherical, we need to have the principal axis that is not known to us. R0 is the principal radius that is not known to us. We have to do by doing the good guess. We have to make an iterative method to find out that what will be R0, and we have varied the principal axis to generate different bubble shape profile. But which bubble shape we will take, that will match with the experimental data. एक्सपेरिमेंटल बबल शॉप जैसे होते हैं उसके साथ मिलेंगे तो दैट R0 will take it for granted. So that way we have done. And when you were, that is another difficulty is you see that because of the existence of multiple solution, as we change the R0, R0 is determined that is we change very carefully. That principal axis that is not known to us. This is the initial guess, and this guess we change very carefully. If you change substantially, you will get the unstable solution. That is the problem with this particular numerical method. So what do? We have changed this R0 very carefully at the order of 10 to the minus 5 of the initial one. As you see that, then you can say that at some stable shape you can get. All right. So this is the how we have done. You see that in the picture that for a different R0, we have got different solution, and which solution we will take, which is matching with the experimental delta, that is for the spherical bubble. And we have another things we have done, that how to calculate the bubble height, that we have done. There is a zone which is giving the gradient, x gradient is less than 1, and you will find the minimum at the neck of the bubble. Last में जो है, that is the neck of the bubble. That last truncated part is the neck of the bubble, and you will find the minimum. And that minimum point will give you you are solving that y versus x, no? So that at certain x you will get the minimum value, and then you will get the height of the bubble. That is how. But this is from, and we have seen that if you are balancing the hydrodynamic force and the surface tension force, then at certain critical radius, you can profile the spherical bubble with the Young modulus equation. That is the capillary equation. After that, it will not work. That we have found where that capillary equation fails to shape the non-spherical bubble. That we have got the criteria. That is basically that that 2 sigma by R0. That is the surface tension force will be greater than delta rho, which is the difference between the gas phase density and liquid phase density, and Gy is hydrostatic force. That means surface tension force will be higher than the gravity force, static force. Then it will be remain spherical. Otherwise, it will be unspherical, non-spherical. Oh no, also have, but I have a couple of slides. Take it. Please give some 2 minutes, 3 minutes. All right. Now, what we done for time of deformation, we have found that when it is deforming, when it is growing stage, by applying that criteria, that when static force will be greater than the surface force, that surface tension force, then bubble will start deforming. At that time, we can say that bubble is going to be spherical to non-spherical. That's what that is the indication that that criteria we have found analytically. That criteria. At the same time, this equation has been solved. This equation this force balance equation is solved by putting the this theory of bubble dynamics or bubble growth, and find out this quadratic equation will give you the multiple solution or the real solution at time t when bubble is deforming. Otherwise, it will give some imaginary solution. So that indicates that it will the deformation is there. At the same time, we have considered some bubble profile to find the bubble shape. Ellipsoidal bubble profile we have picked up. Then we find out the aspect ratio. Aspect ratio is basically that major axis by minor axis. Okay, that is the aspect ratio. That aspect ratio we have found out, and we have this aspect ratio. We put it this in the capillary. That this is the one deformation equation. That psi is the deformation term. And this ellipsoidal profile we have shown that by this equation, this ellipsoidal profile and this force balance equation in terms of the polar coordinate, that has been solved simultaneously. But one problem is there previously people have solved, but BC that is not that can be found by the difference. But what will be the appropriate value of B, that is not known. Initially, we have taken that B is equal to A by A, which is not reasonable. We have published a couple of papers, people have accepted that, but that is not the concern. But this 1.1, this ratio is going to be heuristic one. That is not obeying any physics. Then what we do, we transform this particular deformation equation to the polar form, which is basically called the R by capital R and 1 plus that zeta is called the scaled deformation function and cos phi the polar coordinate angle. We have transformed this equation to this form, and that has been done previously. And then we got this solution in the term of the Legendre polynomial that will give you the scaled deformation function, which is basically minus 3 by 32 Weber number, and that Weber number we use for the that aspect ratio, what will be the A and B, that we can calculate instead of assuming on 0.1. That we have done. This is the new things we have contributed here. That previously B was taken as A by 1.1. That is the heuristics kind of things that people have used earlier and people have accepted also. But now we have theoretical model that should be function, that ratio, aspect ratio should be the function of Weber number, and that theory has been worked out. And accordingly, we have calculated that drag coefficient and this non-shape function. Then this is the algorithm that we have already worked out. This algorithm has worked, and ultimately we are comparing with the experimental bubble volume, whether it is matching that. Then this algorithm first, what is the value of, we are calculating from R minus R to plus R. We are generating the profile. And you see that here a lot of calculation we have done. I am going to quickly to that to give the result, and this is the spherical shape that we have got, and we are matching with the spherical shape with the experimental data, that is matching. Young-Laplace equation is matching with the experimental data, it is matching, but when it is about the shaping the non-spherical bubble, that is not matching, and that we have done here. And here is the plot that is showing how the bubble is deforming, at what time is showing the bubble deformation as the x value. X value is the aspect ratio. This is the point where we are showing that. Yeah, I am winding that. And at the same time, we can show that how that bubble is changing, shape is changing from the spherical to non-spherical, and ultimately the hemispherical or that ellipsoid. That the bubble sequence is at the time that we have generated by the newer method. And this is the comparing with the experimental data that you see. It is our experimental data. Then then we have done some couple of bubble departure. And we have compared with the experimental data, and we have seen that Young-Laplace equation cannot be used to shape the non-spherical bubble. That is conclusion. We have to go through the consider the drag force and by which and also we have to model the deformation to shape the non-spherical bubble, and that we have during the boiling bubble growth and collapse. This is and thank you. Obviously, this presentation I am dedicating to my colleague, close colleague, Viri Kulkarni, Pune and India, and Tunde Ogunaik, Delaware, USA. Those are the two colleagues I have worked with a long time, and they have recently passed it. Okay, so thank you once again, FLAME and 22 and people of Noida, India, and NIT Durgapur. NIT Durgapur nahi dekha to mere travel support nahi milega. Okay, thank you once again. Yes.
In this you have used the aspect ratio. You have written ratio A by B.
This is yeah.
And for that, what you have done, you have used the Weber number.
Yeah.
To relate the A and B.
Yeah.
So can we relate A and B by taking the volume of the bubble also, or
That we are ultimately comparing that, but to derive the theory to get the correct aspect ratio theoretically, then you have to connect with the Weber number. That and you can compare with these things with the bubble volume. Yeah, that is matching more or less, but there is 10 to 20. I cannot say that it is matching, exactly matching, but there is a gap between experiment and theory, 10% to 20% gap is there. We are trying to improve that.
one more thing, in this time we are changing the shape of the bubble. Then
It's during boiling it is changing. During growth sequence, bubble shape is changing.
But one more thing, that is the size of the bubble also will also be important.
Huh.
If we are changing the size of the bubble, then
Depending on the size, we have got some critical size. I got your questions.
I was thinking that you have to put some
Yes, it is there. It is there. I am showing that one. Yeah, some critical size. After that, it is going to be. Yeah, this is the size 3.61 ton. This is the size where that this criteria is there 3.61. That criteria that where that static force is going to be higher than the surface force, surface tensor force.
So you have done this model for nuclear power plant?
No, this is the fundamental work we are doing, and that can be applied to. We are working on the nuclear power plant. That to remove the heat from the fuel rod. Where though that if you are in the nuclear power plant, क्या होते हैं? The coolant is flowing through the channel of the fuel rods, and at the same time you have to extract the heat from the fuel rod surface, and you have to go by the boiling. They can then you can remove the large amount of heat.
But I think you have taken the temperature, changing temperature 27 degrees Celsius.
So that is a superheat. It is the difference between the surface temperature and saturation temperature at what's pressure, corresponding pressure. That is the degree of superheat, not the actual temperature. Actual temperature is something else. Maybe that in a nuclear reactor it will be 249 to 92 range degree centigrade, right?
And is there any possibility that at such a high temperature when we are using the nuclear fuel, that water will be ionized or water?
No. One problem that always there is a loss of coolant is there. What will happen that some locals will continue that when the pressure will decrease. When pressure will decrease, large bubble will form and heat transfer will be less, because when it is going to the flame boiling zone, drastically heat transfer rate falls and melt temperature suddenly shoot up, increases, and obviously they have the alarm also when temperature is increasing. So that things we can do that. But ionization part I am not sure. So I don't know exactly what is happening about the high temperature through to ionization हो सकते हैं. That can be happening. Right? Anything else? Okay. Thank you. Thank you very much.
Thank you all the participants. Now it's time to wind up our technical session for the day one, and I would like to invite Dr. Ravindra Kumar to present thank you gift to our guest.